that I've done so far, every class has been recorded and they're all posted on YouTube. It takes a while to upload a class meeting like this to YouTube. And I'm sure that it's because they're long. I mean, you know, 4 hours, that takes a while. So first it has to be processed from the PIMA, from the Google Meet repository. And then once it's been processed that way, which can take several hours, 2 or 3 hours sometimes, and then I have to move it up to YouTube. That takes hours and hours sometimes. And I'm just assuming it's because it's such a giant file. I mean, a 4-hour long movie is a lot of megabytes, gigabytes, terabytes, whatever, probably gigabytes. But bottom line is that that so far I've managed to get every one of the lectures loaded up there, and they're up there now. Be sure if you decide you're going to watch one of those, you know, and actually if you want to, maybe gather your whole family around the TV, and you know, you guys could all watch it and talk about it, and I'm sure that would be fascinating. I'm only kidding, of course, but I sometimes recommend that if somebody cannot fall back asleep in the middle of the night, they start watching one of my lectures, and you know you will doze off fast. Well, anyway, here we are in the virtual universe, which means I'm sitting in a little studio that's about 93 degrees, and I am, fortunately, I've got a little fan over here that helps a little bit. And we are doing biology class the way we do biology classes these days. That's about the only way to do. You know, I think I said this before, but I'm going to repeat myself and say that, look, if you are enrolled in a Bio 156 class, like this one, then you will be allowed to enroll in a Bio 201 class. The way that the system is set up, it can tell that you're enrolled in Bio 156, and it will allow you to enroll in Bio 201. Now, if you don't end up with at least a C in this class, then they will drop you. The computer will drop you at the beginning of the semester. And thanks, Abril, for pointing that out. I mean, I'm going to make it, as soon as this class is over today, I'm going to send a email to the people who could adjust the schedule. And I'm just going to say, look, the Bio 201 classes are filling up and they need some more. And, you know, they're kind of in the position where they might be able to open some more. The truth of the matter is PIMA's worried about enrollment. Of course, everybody is worried about enrollment these days. And they were conservative when they posted classes, because they were a little bit worried that they would end up with classes with only a couple of students in them. And then they would end up having to cancel those classes and reschedule things. So what they did is they were very conservative in the beginning. They posted a certain number of classes, but once those classes seemed to be filling, I'm pretty sure the plan is to bring some other classes online to meet the needs of people who are having trouble getting in the 201 classes. There are some superstars, anatomy and physiology superstar people that I think are superstars when it comes to teaching anatomy and physiology. I'm talking about people like Ann Haber, Sid Ludt, L-U-D-T, Tom McDonald. I mean, there's just people who their classes tend to fill really fast, and I wouldn't be surprised at all if they were not classes weren't completely filled already. But they are planning to keep on top of that and open classes. But go ahead and do that so everybody who needs to get into 201 can get into 201. Okay, that's the hope. So yeah, I'm reminding you, I am recording, just so you know. I don't know what that could, I don't know why that would end up being a problem, but I suppose if you decided that you were going to just curse me repeatedly and it showed up on the recording, then YouTube might kick the recording off and refuse to have it. Now, I don't know if it makes a difference, but when they ask me at YouTube about posting this stuff, I always tell them that this video was made for children. And I'm not trying to be insulting to anybody, but the truth is that if you tell them a video is made for children, they are not going to put as many commercials and other kinds of breaks in it, I think, is what it really comes down to. So don't be insulted if you see that, okay? All right, so let's get started, right? I'd like to, as always, I'd like to just start by dealing with pure logistics. And, you know, I'm kind of obsessed with that. I want everybody to know, you know, what's going on and all that. Oops, I got to admit a person. Okay. And check them off the list so I make sure that here we go. I lost that PowerPoint. Is it over here? Might be. Might be over here. Yeah, there it is. All right. So here's just the daily agenda PowerPoint for today. And I apologize because I had this up there yesterday, X through Z. And X through Z, I did not cover those questions at all. They have to do with atoms and molecules and the characteristics of living things. And I'm actually hoping to start talking about the characteristics of living things today. Real biology, which I would think would be great to talk about. So anyway, B through N is still all those science questions. X through Z is the beginning of characteristics of life. I hope to get there. I'm just going to mention the metric measuring lab is overdue now, but if you're still working on it, please finish working on it and get it to me. Thank you, everybody who's already done it and sent it in to me. I have been slowly moving through the grading on that. I have a feeling, though, that I'm going to do a lot of grading over the weekends when I'm not meeting in class, you know, so Friday, Saturday, Sunday. So you should start to see grades appearing there soon. I find that during the regular work week, when we are meeting in class, I spend more time refining PowerPoints and figuring out what to do and trying to find my Alka-Seltzer and all that kind of stuff. But as I grade things, I will post those grades on D2L, of course. And so if you can access your grades on D2L, which I'm not sure how to do that, to be honest with you, because I've never accessed a grade on D2L. But I think it can't be very difficult, you know, and I don't have a setup where I can check my grades on D2L. So anyway, we're going to jump right into science very quickly. I would like to, at one point in time, stop and see if we can't gather data for the Alka-Seltzer lab. And what that means is, I think we'll take a physical break. I'm not sure if I'll stop the feed or not during that time, but I'd like it if we could, at some point in time, say, all right, we're going to do the Alka-Seltzer experiment now, and then have everybody do it to the best of their ability. Now, look, if you haven't been able to gather the materials for today, then you know, what can I say? I want to do this lab today and get it checked off the list so that people can turn it in. We will talk about it so much, and I will provide data. You know, we will all provide data, myself included. And if you have been unable to gather the equipment together to do the lab, then you will still be able to complete the lab by looking at the data that we all have, okay? So I'd like to get that done today. I think we're going to be in the position where we can do it, and it'll be as meaningful as possible under the circumstances. Okay? I mean, after all, yesterday I dropped Alka-Seltzer in a glass right here online, and everybody watched it and wondered what the heck I was doing. All right, quiz 1 is already posted. It's due by noon tomorrow. I've already been receiving quizzes back from people, and have recorded some quizzes and recorded the grade. I'm sorry, Kendall, what was the question again? I'll look at it on the chat line. It says,
I have the Alka-Seltzer for cold.
Does it matter? Only have one? Oh, you have the Alka-Seltzer that's for cold. It's Alka-Seltzer Cold is what it's called, right?
Yeah.
Right. Well, you know what? Just go ahead and use it. We'll see what we'll look at your specific data and see if it seems atypical, right? I mean, that's one of the things we can do. I'm gonna open up a document here, and we'll record the data so that we have the entire class's data and each person's individual data. That's going to take some time to do it, but we'll do it. While people are doing that lab, I'll get a way to tabulate the data set up so that we come back after a half hour or 45 minutes or whatever, after people have done the experiment and collected the data, we'll tabulate all the data. As cumbersome as that may be, I think it'd be good to look at all that data. Okay, so just go ahead and do it with that. That would be, we'll just, you have what you have. And again, if you have been unable to get that equipment, then I don't want to make a big deal out of it. I understand that these are difficult times. I'm hoping that most people have the basic equipment that they need, which is not very much. I mean, 2 identical glasses, some hot water, some cold water. If you haven't put some water in the refrigerator yet, then maybe this would be a good time to do it, right? Yeah, that's something we should think about. I mean, if people are, maybe people automatically have some tap water in the refrigerator cooling, but let's say you don't, all right? Let's say you forgot that part, right? Then maybe this would be a good time to stop for a minute, stop the class for a minute, and let everybody go and put enough water for the cold water in your refrigerator right now so it's cooling, okay? I think we should do that because I don't have water in the refrigerator cooling. And I'm the teacher. I haven't done it. So look, that's what we're going to do right now, okay? If anybody doesn't have some water in the refrigerator cooling already, tap water, remember, it has to be tap water. It's not your expensive Fiji water. And we're not doing the Fiji water experiment here. We're doing a tap water experiment. So that's what we're going to do right now. I'm going to personally do it too because I haven't put any water in the refrigerator. I'm going to go get some water and I'm going to put it in the refrigerator so I have cold water ready to go. All right? Look, how long is this going to take? 3 minutes, 5 minutes, whatever. Let's do it. Probably took about a minute. Now I have some tap water. I don't know what temperature it is. It's sitting there in the refrigerator in a little glass. I'm probably going to use 100 milliliters of water just because that seemed to be a good amount of water to use for the little glasses that I have. So, so I put more than that in a little glass, put it in the refrigerator. It's 135. And so it'll be sitting in there for an hour by 2:35, which is, let's hope that we can stretch things out so we're ready to go with the experiment in about an hour, okay? So I'm going to be really patient, just patient for a minute. I'm assuming it's not going to take people that long to go get some water, put it in a container, and throw it in the refrigerator. I mean, not throw it in, but just carefully place it in the refrigerator. Anyway, that way we've got the experiments kind of working. In the classroom, I would have set that all up already. I would have had bowls of ice water. And it would have had water heating in a big old Erlenmeyer flask so that we'd have warm water. But, you know, in a classroom, I never wanted to have boiling water. Boiling water is fine for some things, like, you know, if you're making pasta, but it's not good to play with because you can get pretty seriously burned. So I never wanted to have water in my classroom. I tried to set the water in the classroom to be about maybe 45 degrees centigrade, which is, gosh, it's about, let's say 45 degrees centigrade is about 120 degrees Fahrenheit. Ugh, there's my calculator. Right? Again, you don't need to do these calculations, but 45 times, whoops, so, yeah, 45 times 1.8 plus 32 equals 113 degrees. And you know what? It was about as warm as a really hot shower. So nobody was going to get physically injured by it. And today, when we go to get warm water, we're going to run the tap and get it as hot as we can by running the hot water tap, you know, for, I don't know, 30 seconds or a minute or whatever, and get it pretty hot. And that's what we're going to use for our warm water treatment. Okay. In fact, you know, I kind of put some of this stuff together here. I have not posted this document. I don't know if it's worth posting it or not, but just real quickly, take a look. Remember, our research question was, will Alka-Seltzer dissolve more quickly in warm water or cold water? Then we sat and talked our way through this, and we revised the question this way: will Alka-Seltzer dissolve more quickly in warm water than cold water or water? And then look at all the little caveats. The asterisk means we could be using brand name or generic Alka-Seltzer. I think that we're probably using brand name Alka-Seltzer in all of our conditions. We will define dissolve. We define dissolve as when the tablet is completely disintegrated. And honestly, this is the thing about science. You may look at this and go, you know, Steve, if I was doing that experiment, I would do it differently. I would decide that it was okay to stir it, and I would define dissolve as zero scum, zero sludge, zero bubbles, and all that. And I would say, great, that's just a different experiment, one that could be valuable to do. Here's what we decided as our criteria for more, that there must be at least a 10-second difference between the time to dissolve in warm and the time to dissolve in cold. Otherwise, guess what we will do? We will accept the null hypothesis that there is no difference. If there's only a 9-second difference between the time to dissolve in warm and the time to dissolve in cold, we're going to decide that that's not a real difference. It's too small. And so we're going to declare that there's no difference. And no difference sounds to me like null hypothesis. Okay. The definition for warm and cold is this: cold is water refrigerated for 1 hour. That's why I stopped a minute ago and asked you to go and put some water in the refrigerator. And warm is hot running tap water. So, you know, nobody's going to be injured by any of the water here. It's not going to be as cold as I might have had it in the classroom, and it's probably not going to be as hot as I might have it in the classroom. But I feel like we will have warm and cold pretty distinctively different. If we had centigrade thermometers, we could measure that temperature. If you have a centigrade thermometer available and you want to measure that temperature, that will be great. I will measure the temperature of the water that I use because I just have one of those kitchen thermometers. You know, it's electronic. You put it in anything, you know, it'll give you the temperature. I mean, you use it to stick it in a steak to tell you that it's 160 degrees inside, but it measures pretty well in a broad range of temperatures. And it's just a little electronic kitchen thermometer. And Kendall has been in the culinary program, and so he probably has one of those. He already said that he had one of those thermometers like that. So if you have a thermometer and you want to get some actual numbers, that would be great. But otherwise, we will have these two categories, cold and warm. And then what would you mean by water? Well, I know it sounds weird, water. We know what water means. What we mean is tap water in this case, not distilled water. not some grubby old pond water that we found out in the street, not water that we use to wash the dog with. No, we're talking about tap water straight out of the tap. Okay, Tucson tap water, right? Which I don't generally drink Tucson water. I use it for cooking. I don't generally drink it. So then take a look at what I've done below this. Okay, I started to write hypotheses. Remember, in a certain sense, hypotheses are somewhat general and they apply to many cases. So here is the null hypothesis. Remember, the null hypothesis always states there's no difference. Okay, no difference in the time to dissolve in warm and cold water. That the time to dissolve in warm and cold water will be the same because the difference will be less than 10 seconds. Now, alternate hypothesis 1, you can guess. If this one says there's no difference in the time to dissolve, well, then the alternate hypothesis say, well, there is a difference in the time to dissolve according to our criteria, and the time to dissolve, that's what TTD stands for. Time to dissolve is less in cold water than in warm water. All right, so time to dissolve, less in cold. Alternate hypothesis 2, well, I think you guess what it is, right? It's going to sound just like this. It's going to say, alternate hypothesis 2 states there is a difference and the time to dissolve is less in warm water than cold water. Those are the 3 standard hypotheses. But could there be an alternate hypothesis, another one? And you know what the answer is. Of course there could be. It's probably not going to be a very good one, but there are always alternate hypotheses, always. Some of them are just plain stupid. Okay, that's the only way to put it. Some of them are just plain stupid. So, so there we go. We've got hypotheses. Now, predictions. Predictions are something we need to talk about, so let's go there. Okay? I didn't even stop talking for 1 second. Were there any questions at all about the agenda for today and the kind of stuff lingering in the background? Are people still putting water in the refrigerator? I hope not. It shouldn't take that long.
I have a quick question, Steve.
Sure, go ahead.
For the YouTube videos, is there a link off of D2L, or do I have to, or is that off of the MyPima, like the link?
No, there is no link off D2L, but you know what? I can post a link off D2L, I'm sure. I just haven't done it. So let me explore that option because it would be great to do a link off D2L. I mean, I know it just never occurred to me. So thanks for asking.
Of course.
I'm sure it's no problem. I really think that, once I have emailed people the links, most people I think are just going to do this. That's why I put this, I wrote this thing here, Stephen Mackey Bio 156, because that's the best way to access them. When you go to YouTube, you just go to youtube.com. There's a search line right there at the very top. And then you just put in Stephen Mackey Bio 156, and it takes you to a bunch of lectures that I've posted. So, in the future, if you don't have anything to do, there's many, many lectures there that you could listen to. But the bottom line is that, of course, I can extract a link from those, and I could post it on D2L. I just need to figure out where to post it on D2L. And as I've admitted from day one, I'm learning D2L as fast as I can while teaching at the same time. And, I don't know. Okay, but thanks for that suggestion. I will do it. That would be easy. I did post a link. At one point in time, I posted a link here, but I thought, well, you can go and search them out this way. But it would be nice to be able to click on them somewhere on D2L, wherever it seems like the appropriate place to put them, even if it's just a document that says, here's the links to the lectures, I mean, I could certainly post that. So thanks for that suggestion. I will work on that. Okay. I'm shutting my mouth because I know it's hard to sometimes get a word in edgewise with me. That's the 17-second rule, right? I don't know where, I forget where I read this. You should, when you ask a question, you should pause for 17 seconds. That's a long time. I mean, it's literally, that's so long that it makes people nervous. And they go, I'm going to ask a question. I'm going crazy. But, so sometimes that's what I have to do personally because I can gab incessantly. Okay, so here we go. Where did I want to go next? I wanted to go to science and the scientific method. So this PowerPoint, I'm going to set it, I'm going to open it up as a regular slideshow, and I'm going to go from the current slide. I don't think we need to go back all the way to the beginning. This is review. We're just reconnecting with where we were yesterday. Here's step number 3, create multiple hypotheses to make a list of possible answers to the research question. Well, we already saw this. Hypothesis is one of the many possible answers to a research question. You know, there is a zero doubt in my mind that I will ask for the definition of a hypothesis on the next quiz. Okay, there's zero doubt. There will be that question. And honestly, if somebody tells me a hypothesis is an educated guess, and that's it, I'm not going to give credit for it because it's too vague and imprecise. What you want to say, you could say a hypothesis is an educated guess about the possible answers to a research question. Absolutely, you could. Okay, but to just say educated guess is too vague, and I know that somebody in another science class once told you what educated guess means. You know, like, or they once told you, yeah, hypothesis is an educated guess, because I've heard that too, and I just think it's a weak definition of a hypothesis. Here's a good one. It could be a great hypothesis, an awful hypothesis, a stupid hypothesis. It's always true. Hypotheses, like I said, tend to be general. And what I mean about that, and you'll see this, when we generated the null hypothesis said, look, there's no difference in the time to dissolve in warm and cold water. Didn't tell you anything about what temperature the water was, how much water was used, any of that kind of stuff. It was pretty general. Again, I'm going to say it, it's best to start with a long list of hypotheses and hope the best answer is somewhere on that list. Science is really good. The scientific method is really good at taking a long list of hypotheses and shrinking it down. That's what we want to do. We have 50 hypotheses, we shrink them down. I mean, some questions that we have have a sort of limited number of hypotheses. I mean, like the question of why won't my car start? I mean, there's not 200 hypotheses. There's a few good hypotheses. But, you know, what if you had a question like what causes cancer? How many hypotheses could you generate to that particular question? I mean, there's probably, you could probably generate 20 hypotheses, and there's probably at least 6 or 7 of those that seem to be pretty good hypotheses. When you ask about what causes cancer, one hypothesis is it's caused by carcinogenic substances in the environment that you get exposed to. Carcinogenic means cancer generating, right? So you're exposed to carcinogenic substances in the environment. Another hypothesis is that your genes can actually cause cancer. Another hypothesis is that viruses can infect cells and cause cancer. Another hypothesis is that bacteria can invade cells and cause cancer. Another hypothesis is that electromagnetic waves, like UV light, can cause cancer. Another hypothesis is that that stress and anxiety causes cancer. Another hypothesis is that cancer is caused by karma, and that because you were really mean to your dog in your past life, you're going to get cancer in this life. I mean, I'm just saying there's lots of hypotheses, and we have a really long list of hypotheses about cancer. What we want to do is shrink that list to be as short as possible. There won't be one answer. There won't be one hypothesis in the end. There will be multiple hypotheses, but we're going to take a long list and shrink it. We start out with a long list. We hope the best answers on that list, and we start shrinking the list. So, properties of a good hypothesis, just to mention them again. Hypothesis is valid. It answers the research question. It makes logical sense. It accounts for the known facts. A useful hypothesis is testable. It can be used to generate predictions about the measurable, countable, weighable world. A hypothesis is falsifiable. This means that you can show it has made a false prediction, and the hypothesis can be rejected. Just so you know. And then, of course, we did this thing with our car yesterday. So then we talked about these famous and important hypotheses to consider. Now, in most cases, when we're doing the kind of experiment we're doing now, it will be very clear what the null hypothesis is, and it will be pretty clear what the alternate hypotheses are. And what's great about this as a critical thinking tool is, if you've never heard this stuff before, well, then you're going to be confused by it, of course. If you've never heard these things before, you're going to go, what the heck? No hypothesis, alternate hypothesis. But the more you think about it and the more you apply it to some real world examples, the more it will make sense to you. That's the only thing I can say. You know, I mean, this is some new vocabulary for most people. They've never really thought about this before. But I'm going to once again tell you something. Everybody seems to think that we need to learn how to critically think better. I hear this all the time. We don't provide enough experiences for our students so they get an opportunity to do critical thinking. Because in the real world, we need to do critical thinking. Employers want to hire people who can do critical thinking. Well, I have to tell you, teaching critical thinking is not as easy as it sounds, except that the scientific method is critical thinking. It's one kind of critical thinking. It's not the only kind, but it is absolutely a type of critical thinking. And if you understand the scientific method and you can use the scientific method, then you will be critical thinking. And nobody just learns the scientific method in 5 minutes. Nobody does. I didn't. I've learned the scientific method because I've been really lucky to have great science teachers. And I went to grad school to study science, and I did science and worked with scientists and still work with scientists, etc. So it rolls off my tongue, but believe me, it's not. If you're having trouble comprehending it, then that's fine. That's normal. That's totally normal. Again, these days, I don't know about you, but if I have trouble comprehending something, I'm just like, I just can't understand this concept, and it's swirling around in my head, I go to my toolbox, and I don't ask my mom about it because she doesn't know anything about it. I really don't want to ask my doctor or lawyer about it because I don't know that they know that much about it, though doctors are scientists. They should know about it. I'm going to go to Google, and I'm going to Google scientific method, or I'm going to Google null hypothesis, or I'm going to Google hypothesis. And then I'm going to be careful because somebody on Google is going to tell you a hypothesis is an educated guess, and they're not even going to tell you what it is about. But you know better. You know what a hypothesis actually is. And so, I mean, we're so lucky these days because we have access to this incredible global database at the tip of our fingers on our cell phone. I mean, you're sitting in the doctor's office, you're bored, you don't know what else to do. You could Google hypothesis. You could Google cellular respiration. I mean, whatever. I mean, we live in amazing times. And I don't know, if you're born with all this stuff at your fingertips, you may take it for granted, but I wasn't born with any of this stuff at my fingertips, so I'm not going to take it for granted. All right. So, again, we did this stuff yesterday, famous and important hypotheses. And I don't think there's any reason to go over this. I mean, we all know the answer to this question. Are cats smarter than dogs? Of course, cats are smarter than dogs. I mean, I have a dog, I have cats, and cats seem smarter to me. But I'm sort of joking. I mean, the bottom line is that I don't know how we would actually do this experiment. All right, so now the next step, that's what we need to think about today, is to generate predictions or deductions from our hypothesis. I'm going to put this on the chat, I think, because there's a word that I should have embedded somewhere in this PowerPoint, but I didn't, okay? And the PowerPoint is this. This is what I want to write. I want to write this word, induction. Okay? Induction is a thinking process. It's a logical thinking process. I'm going to post this in a second. Logical thinking process, where you generate possible answers to a question you have. That process is called induction. And humans do it all the time. I mean, we constantly do induction. We have a question, like, I don't know. I mean, it could be as simple as, what are we going to eat for dinner? And then we start generating a list. All right, let's have a cheeseburger for dinner. Let's have pizza for dinner. Let's have a gigantic salad for dinner. Let's eat artichokes for dinner. I mean, you're generating possible answers to a question. We do it all the time. I mean, when we're younger, we might think, how can I get a girlfriend? What can I do to get a girlfriend? And then you do a little observation, you watch TV, you read a book, you ask your friends, and then you start generating a list of possible answers. Like, maybe if I had a car, I'd be more likely to get a girlfriend. Maybe if I had a cat, I'd be more likely to get a girlfriend. Maybe if I had a job, I'd more likely to get a girlfriend. Or maybe if I just had a bunch of money, I'd be more likely to get a girlfriend. Now, in my case, I remember reading very distinctly that men with beards had no trouble finding girlfriends. And so I grew a beard, and it didn't work. But the bottom line is that the thing is that we're always doing it. It's something we always do. We do induction. We have a question, and we start generating possible answers to it. It is a thinking process that we do all the time. Okay, now go back to where we were here. Deductions are something different than inductions. When you generate hypotheses, you're doing induction, right? When you generate predictions, you're doing what's called deduction. And when I hear the word deduction, I think about Sherlock Holmes. So hopefully I'll remember to talk about Sherlock Holmes in a few minutes. But predictions are related to hypotheses. They come after hypotheses. You use hypotheses to generate predictions. But here's the thing. While a hypothesis is kind of a general thing, like Alka-Seltzer will dissolve more quickly in warm water than cold water, or there will be no difference in the time to dissolve in warm and cold water. Those are general. Predictions have numbers, details in them. They're specific. These predictions are about real, countable, measurable, weighable events, things we can actually measure. So there's a formula for creating deductions or predictions. It looks like this. If I pretend a certain hypothesis is true, like if I pretend the null hypothesis is true, then what should I observe, count, measure, weigh in the real world if this hypothesis is true? And I mean, it is a mental thing because we don't know if the null hypothesis is true. We don't. We don't know if alternate hypothesis 1 is true, but we're just for a minute going to pretend. This is what deduction is. We're going to pretend it's true. And then we're going to say, well, if it was true, then what should I be able to count or measure and weigh in the real world? So let's take a look. Here's one here. We're going to generate predictions. Remember hypothesis 1 about our car? Car is out of gas? Well, if hypothesis 1 is true, then when I look at the gas gauge, it will read empty details. I'm looking at the gas gauge of my car, and I'm examining the little, dial, and the dial, the arrow, whatever, and I'm looking at the position of the dial. You know what I mean, right? If hypothesis 1 is true, then when I look at the gas gauge, it will read empty. Okay, what about this one? Here's another possible one. If hypothesis 1 is true, then when I put some gas in the tank, the car will start. So notice, if you would, here, I started a prediction always with if. If then. If cats are smarter than dogs, then when we give an animal IQ test to 10 dogs and give an animal IQ test to 10 cats and compare the averages of those IQ tests using a t-test, the t-test will declare that there is a difference between cats and dogs, and cats have the higher IQ number. If then. So one thing about a prediction is that almost always predictions start with the word if. And if you look at a prediction, you'll see, if I pretend a hypothesis is true, then what should I be able to measure, count, or weigh? Measure, count, or weigh, and what we're doing there. That's the bottom line. If a hypothesis, we're only pretending that hypothesis 1 is true because we don't know that it's true. But in order to generate predictions about the real, countable, measurable, weighable world, we sort of have to mentally pretend that it's true. You see how I put the true in quotes? Because honestly, that hypothesis will never be true. Even if it makes 100 true predictions, we will not consider that hypothesis to be true. Okay? How about this one? Just take a look and think about this for a minute. Thought, hypothesis 4, the battery is dead. Somebody out there in the listening audience, please, generate a prediction about this. Where am I? Oh, wait. Darn it. I didn't want to do that. I didn't want to show those predictions. Sorry. So would somebody who has great courage open their mic and tell me a prediction from this hypothesis? Yes, go ahead.
If the battery is dead, when I turn the key, there will be no lights or radio in the car.
That's very great. That is very good. Perfect prediction. It started with the word if, right? Because I'm just pretending. If hypothesis 4, that the battery is dead, is the reason my car won't start, then when I turn the key, I will see nothing electrical working, right? That's pretty much what you said.
Yeah.
Right? The battery won't work, the lights won't work, nothing will come on. Oh, believe me, I've experienced this before. Okay. So great. That was a great prediction. Anybody else want to try? And I mean, here's the thing, just so I mention this. If you have a hypothesis like this, you can use most hypotheses to make lots of predictions. Lots of predictions. And I'll show you some specific examples in a minute, but okay, so one prediction is that you turn the key and the lights, no lights come on. Okay? Can someone else think of a different hypothesis? Sorry, not a hypothesis, a different prediction. If hypothesis 4 is the best, then what?
If the battery is dead, then I replace the battery and then the car starts again?
Yes, very nice. Sure, another great, I mean, that's another great hypothesis. Okay, anybody I want to try? Sorry, did I say hypothesis? I meant to say prediction. I guess I haven't had enough soda yet today. Yes, that was a great prediction. If hypothesis 4, that the battery is dead, is best, then when I replace the hypothesis, when I replace the battery, when I place the battery, the car will start.
Okay, I have one. If the battery is dead, when I hook it up to the slow charger overnight, it should be fully charged in the morning.
A great prediction too. So all of those are great predictions. And I mean, again, you can generally make a long list of predictions. Like you could say, well, if hypothesis 4, the battery is dead, is best, then when I get a machine that measures battery power and I hook it to the battery, it's going to read numbers that tell me the battery's dead. Or if the battery's dead, when I call AAA and they come out and test the battery, they'll tell me the battery is dead. If the battery is dead, then when I go and buy a new battery and put it in, it'll work. So I don't know. I'm trying to remember what predictions I put then. If hypothesis 4 is true, of course, I'm putting true in there. I'm putting true in quotes because I'm going to tell you this again. We're not going to ultimately declare hypotheses to be true. But if hypothesis 4 is true, then when I test the battery, it will be not producing enough current to start the car. If hypothesis 4 is true, then when I replace the battery, the car will start. Very nice. See, honestly, I think that once you start thinking this way, it helps organize your thinking about certain things. Again, are you going to be able to use this are you going to be able to use this process to answer every question that you have? Of course not. No process in your toolbox will answer no tool you have in your toolbox will answer every question. That's why you want to have multiple tools. I mean, in your toolbox, you have a hammer, and that has certain kinds of, you use that into certain cases. In the toolbox, you have some pliers, whatever. Taking toolbox too literally, but you know what I mean. You have multiple tools. You don't, well, my father would say, use the right tool for the right job. And that's what we're doing here. Now, I'm not going to teach you how to meditate. I'm not going to teach you how to write poetry to answer questions. But scientific method is one way to do it. And because we live in a pretty concrete, measurable, weighable world, then a lot of times that process is helpful to us. Not always, but it is helpful to us. So I'm going to go back here because here are just some predictions. Some predictions about the Alka-Seltzer lab. Now, look, these look a little bit more specific than we're going to be able to generate, but that's okay. I think when you look at them, you'll understand that these are examples of predictions. So take a look at what the first prediction says. It says, if the null hypothesis is true, in quotes, then when we drop 2 grams of Alka-Seltzer in 50 milliliters of water at 5 degrees centigrade and carefully measure the time to dissolve, then repeat this process for 35 degrees centigrade, there will be no difference in the time to dissolve in these 2 experiments. I mean, what I'm hoping you'll see in here is, look, 2 grams, 50 mils, 5 degrees, carefully measure the time to dissolve. In the classroom, we would have used a stopwatch. Maybe today when you do it, you use the stopwatch on your phone or a watch. There will be no difference, and no difference, the 2 means we use some criteria, in this case, 10 seconds. And honestly, even in the classroom, when we did this in the classroom, people would use numbers like 10 seconds because we can't do a statistical test on this one little data set. So if the null hypothesis is true, then we drop 2 grams of alcohol, blah, 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 right? Now, how about this? Here's one prediction of the alternate hypothesis 1. If the alternate hypothesis 1 is true, then when we drop 2 grams of Alka-Seltzer in 50 milliliters of water at 5 degrees centigrade and carefully measure the time to dissolve, then repeat this process for 35 degrees centigrade water, there will be a difference in the time to dissolve. In these two expressions, there will be a difference. Remember up here it said there will be no difference. Why? Why no? Because this is the null hypothesis. That's why. The null hypothesis always says no, no difference, no change, no relationship. That's what the null hypothesis always says, okay? There will be a difference, and the time to dissolve will be less for the Alka-Seltzer in the cold water. So I want you to notice that when we made these predictions, they're very specific, and to a certain degree, they're related to the experimental design. Meaning when we actually do the experiment, when you read these predictions, don't you think, oh, I know exactly what I'm going to do? And that's because you've sort of pre-thought what you're going to count and measure and weigh. That's super important. You're going to pre-think it in order to make predictions, because predictions are specific. They include details about the countable, measurable, weighable world. Now, let me just point something out I said before. Remember I said before that a good hypothesis will generate lots of predictions? Well, just think about this for a minute. Here's one prediction of the null hypothesis that is, part of this Alka-Seltzer lab. If the null hypothesis is true, then we drop 2 grams in 50 mils at 5 degrees. Well, couldn't I have just written this when we drop 2 grams in 100 mils of water at 5 degrees, 2 grams in 200 mils of water at 5 degrees, 1 gram in 50 mils of water at 5 degrees, 1.5 grams in 50 mils of water at 5 degrees, 2 grams in 50 mils of water at 6 degrees, 2 grams in 50 mils of water at 7 degrees. How many different predictions could we generate that from this hypothesis? And I mean, you heard me. I changed this number. I changed this number. I changed this number. How many different iterations could I do of this predictions? Oh, so Emily, where it says here, when writing our predictions, you can just write H sub 1 for alternate 1 and H sub 0 for null hypothesis. Absolutely. You don't have to write out null hypothesis each time. Okay, but I lost that document. It's over here. Yeah, I think what you can see is that, look, there could be about 1,000 different iterations. I mean, a hypothesis like the null hypothesis, when we consider it in the context of this Alka-Seltzer lab, we could do 1,000 different predictions from it. Hypotheses make a lot of predictions. They can make lots and lots of predictions. Now, before we leave this page, let me just scroll down for a minute and show you something that, oh, well, here we've got H sub 1. These the same. T job will be less for the Alka-Seltzer and T will be less for the Alka-Seltzer and what? Yeah, these look like the same to me. Don't ask me why. I'm going to change this to H sub 2. Okay. If alternate hypothesis 2, then we do the exact same thing, and there will be a difference in the time to dissolve for the Alka-Seltzer in the water at 35. That's the warm water, right? So, bottom line is one thing that's worth noting about this, and I'm sure you've already noticed, is, do you see I did the exact same thing here and here and here? I mean, notice I did the exact same experiment. So really, what's great is I've got my 2 containers, and I've got my 2 Alka-Seltzer tablets, and I have my cold water, and I have my warm water. And I plunk the Alka-Seltzer in the cold water, and I time how long it takes to dissolve. and I plunk the Alka-Seltzer in the warm water, and I time how long it takes to dissolve. And I have actually then tested all three of these predictions at the same time. That is, well, that's a good thing to do, right? You don't want to have a different setup for the null hypothesis and for alternate hypothesis 2. Somebody would say, wait a minute, why didn't you just do the same experiment and use that experiment? You do that one experiment and then use it to test all three predictions. So let me ask you a question now. When you look at these predictions, we've got three predictions here. Can these predictions all be true? I mean, can they all be true? When you do this experiment, is it possible that there will be, Thelma, TTD stands for time to dissolve, okay? And here's the thing. I don't think actually all three of these can be true. How is it possible that there can be no difference and a difference at the same time? How can there be a difference, but it dissolved faster in cold water and it dissolved faster in warm water at the same time? When we do drop Alka-Seltzer in water, it seems to me that there's either going to be no difference or a difference. And once we discover there's a difference, we are going to say, okay, the time to dissolve was less for cold water, or the time to dissolve was less for warm water. So, you know, the reality is that we've got these three predictions, and when we do an experiment based on these predictions, in the end, we're going to declare that, well, probably we're going to declare that one of these predictions is true, and two of these predictions are false. And maybe you remember from way back when, well, we'll go back to this in a minute. Now, let me just show you what I did down here. This is sort of a way to write it out a little bit easier. So you don't have to write the whole darn thing every time. I wrote here, if the null hypothesis is best, if the alternate hypothesis 1 is best, if alternate hypothesis 2 is best, then when we have 12 Alka-Seltzer tablets and 125 milliliters of water at 5 degrees centigrade and at 35 degrees centigrade and carefully calculated time to dissolve, there will be, well, the null hypothesis will say there's no difference in the time to dissolve. Alternate hypothesis 1 says, yes, there is a difference in the time to dissolve, and it's less in cold water. And alternate hypothesis 2 says, yes, there is a difference, and the time to dissolve is less in warm water. So you see how instead of having to write these things out 3 times, I was able to sort of create a little summary, but it has if, then, 3 hypotheses, and the 3 predictions of those hypotheses. So, you know what, I'm going to post this document, okay? I'm going to post this document so that you can consult it, save the changes I made to it, and I'm going to post it so that you have access to it. How am I going to do that? Well, the easiest way is for me to go to my courses, go to Drive. Here I am on Summer Session B, opening it up. I'm going to post this document as document number 11 here in case you want to consult it when you're working on the lab and getting ready to turn it in. Can I actually do that? Yes, I'm sure I can. I must be able to, please. I think it's here. What did I say? I was going to post this as document number 11. Sorry, folks. I wish I was better organized. But sometimes, just like in a real classroom, you think of things at the last minute and you don't get them done. Well, but I'm doing it now. So when you are writing this, when you're working on the lab write-up for this, you should be able to consult this document should you wish to consult it. Okay. It's listed there now as document number 11. I'm back. Okay. So I'm going to go back to this. We did this already. Then we've figured out how to generate predictions. And there we go. I got to tell you something kind of scary about hypotheses and predictions. A hypothesis will generate a lot of predictions. Oh, I'm sure there are some hypotheses that don't generate many predictions, but most hypotheses, they can generate a lot of predictions. And the scary thing is this, that a hypothesis can generate hundreds of true predictions, but still be a bad hypothesis. What? You heard me right. A hypothesis can generate hundreds, thousands, millions of true predictions and still be a bad hypothesis. That is a little mind-blowing to me, but I assure you it is a fact. How is it that a hypothesis can make millions of true predictions, but still not be a good hypothesis? And honestly, I sort of think the answer is that it can do it sort of by accident, amazingly enough. Now, look, let me give you my favorite example of this. In fact, you know what? Let me just look, because I think let me just go over here. Here it is right here. I'm going to have to bounce around a little bit. I probably reposition this slide. Here's a disturbing idea. A bad hypothesis, one that should be rejected, can make millions of true predictions by accident before it is ultimately rejected. Now, I'll tell you what that means. It means that in science, we are really, really careful about declaring a hypothesis to be the best hypothesis, the true hypothesis. We just don't do that because we recognize that a bad hypothesis can make millions of true predictions before it's ultimately rejected. And my favorite example, the example I was going to give you, was what's called an example you've heard of. It's famous. It's called the geocentric hypothesis. It says that the Earth is the center of the universe. And it was first proposed in 150 AD, and it was accepted until the 1800s. So for hundreds of years, it was not just said that the Earth was the center of the universe, but everybody thought it was true. And it was written into laws, and it was written into religious doctrine. But everybody knows now the Earth isn't the center of the universe. The Earth isn't even the center of our solar system. I mean, we know that now. So what happened in the 1800s when it was finally replaced? I mean, it was finally demonstrated because it made false predictions that it was not true. Well, it was replaced by another hypothesis called the heliocentric hypothesis. So the reality is that we need to be careful about hypotheses for sure. Okay, we need to be careful about hypotheses for sure.
I have a question.
Yes, go ahead.
Now, my thing is this, not to get political, the whole flat earther movement that's being revisited by most people.
Right. Well, no. I wouldn't say it that way, really. I wouldn't say it's being revisited by most people, would you? I'd say it's being revisited by a few people.
Yes, a few
That's how I
people. They post all these things online showing that the earth is flat. I'm just like, come on now.
Right. Well, the flat earth was a hypothesis for hundreds of years. And then explorers went out and they started exploring. They could not find the edge of the earth. I mean, this is a big one. If the earth is flat, then let's say that's a hypothesis, the earth is flat. Well, then here's my prediction. If the earth is flat, you should be able to walk to the edge of the earth and look over the edge. And people did this. People went everywhere. They took boats. They took, they could not find the edge of the earth. And of course, the flat earthers said, well, you just didn't go far enough. Well, the bottom line is that if you have that hypothesis and you make predictions, you will find that does that hypothesis generate some true predictions? So, should say it wrong. Does that hypothesis that the earth is flat, can it generate some true predictions? I think it can, okay? But what I said a few minutes ago is what's most important here. A hypothesis that is bad can still generate true predictions. But the bottom line is the minute a hypothesis generates a false prediction, then that hypothesis is trash. I mean, unless you could look at that prediction and go, well, that's just a stupid prediction. But no, scientists would say, look, let's make some good predictions from the flat earth hypothesis. The earth is shaped like a disc, right? So then we should notice certain things. And again, I think it's a great example. I know, Kendall, was that you who proposed that example? I'm going to say that's a great example because some people still argue about this, even though we have airplanes that fly around now, when we have satellites that circle the earth. I mean, if the earth was flat, wouldn't satellites be able to perceive that and show us data around that? Of course they would. So I've never really the flat earth idea, I think it's really a sort of symptom of an anti-scientific philosophy in which, look, I don't care what science says. I'm going to believe that that cats are smarter than dogs, no matter what the darn IQ test says. So anyway, that's that fits in perfectly to the scale here. I'm sure there are some predictions of the flat earth hypothesis that are true, but that doesn't prove it to be true by any means. Because as you already know, a bad prediction can make millions of true hypotheses by accident. And as long as it's making true predictions, we think, well, it might be true, it might be true, it might be true. But eventually, bad hypotheses make false predictions. And once you've made a false prediction, well, then I'm backing up here, I'm going back to this. Sorry. Remember this? Shove this up right up front so that we had a little bit of a framework. Hypotheses make predictions. We test predictions doing our experiments. We analyze experiments. The predictions, if they're created well, we're going to be able to declare predictions true and say that supports the hypothesis, or we're going to be able to declare predictions false, and that's going to take the hypothesis and falsify it, reject it, and throw it in the trash. That's the way the scientific process works. Sorry for zooming like that. Mwah. Oh, I went way too far. Okay, so anyway, we're back here generating predictions from our hypotheses. Now, remember, when we generate predictions from our hypothesis, we have to think about experiments. Because experiments, step number 5, is how we test our predictions. That's what we're going to do today. We're going to do an experiment to test our predictions, right? If the null hypothesis is the best hypothesis, then when I drop one Alka-Seltzer tablet in 100 milliliters of cold water and time how long it takes for the tablet to disintegrate, and I drop one tablet of Alka-Seltzer in warm water and time how long it takes for the pill to disintegrate, there will be no difference in the time to dissolve according to our criteria, the 10-second difference, and there will be no difference. That's what the null hypothesis says. So that's an experiment. Now we're already thinking about our experimental design. But step number 5, we have to establish a clear and repeatable experimental design related to the research question, the hypotheses, the predictions to be tested. Now, I don't know, maybe I should have pushed this a little further up in line. I don't know. This is a brand new PowerPoint that I just wrote. Normally I would do this in class, so this PowerPoint may need to be rearranged. But when we look at our research question, we have to identify the important variables. And this is something we always think about when we're doing experiments, which is why I placed it here. It might be that this is something I should have pushed in a different format up a little bit earlier, but I didn't. So here we go. We're going to identify an important variable. Remember what the research question was? Of course you do. The research question was, will Alka-Seltzer dissolve more quickly in warm or cold water? Okay, that is what we call a 2-variable question. And in a 2-variable question, there is always one variable that's called the independent variable. I abbreviate the independent variable as IV, independent variable. This is the variable that is deliberately created or set up by the researcher. Okay, this is the one we create. So whatever it is, it has to be within our ability to create it. So let me just ask, can somebody think about the research question that we're working on and tell me what the independent variable is, and let me give a hint. Why did we put water in the refrigerator? There's my hint. What is the independent variable in this experiment? Would some brave soul activate their microphone and take a chance at it? I'll be gentle if you're wrong. The independent variable is the variable that we are going to set up ourselves. It will be a variable. Go ahead.
Independent variable in our experiment is the water that we put in the fridge.
Okay, but it's the water, but what is it about the water?
It's the temperature of the water.
Exactly, thank you very much. It's the water temperature, right? I mean, that's why I gave that hint. We went to the refrigerator because we're creating cold water, right? By putting it in the refrigerator. And we can create warm water and cold water. I mean, that we want some warm water and we want some cold water. The independent variable is water temperature, and we want warm water and we want cold water. And I don't know about you, but I can absolutely set it up so I have one glass with cold water and one glass with warm water. That's well within my ability to do. You too, right? I mean, everybody could do that. The independent variable is something you set up. Okay, now the dependent variable, I abbreviate it as DV, is the variable that might be related to the independent variable and change during the experiment. Usually, all we can do is measure the change in the dependent variable. We don't set the dependent variable up. We just observe it. So in this experiment, I'm going to say, what are we going to actually measure? There's my hint. What will we be measuring? I mean, I've said to people, look, we're going to need to measure this as part of the experiment. Does anybody remember? Well, would anybody be willing to jump in and say, Steve, this is what we're going to measure. That must be the dependent variable.
Will we measure the water, like 100 ml?
Oh, you know what? We will measure the water, but when we look at the research question, there's nothing about how much water in it, right? So it's something else we're going to be measuring, and it's
We're
something.
going to be testing. Sorry, we're going to be testing a difference in temperature, so that's what we're looking for.
Well, remember the temperature difference was the independent variable. So the dependent variable is something we're actually going to measure. You know what? Yesterday we measured it.
Oh, the time that it takes to dissolve.
Exactly. That's what it is. It's the time to dissolve. Now look, I'm going to tell you that I have no ability to manipulate time. I can't scream at an Alka-Seltzer tablet and say, listen, Alka-Seltzer, I paid $3.59 for you, so you dissolve fast. Right? No, I mean, I can't. I don't have any ability to manipulate time. All I can really do is drop the Alka-Seltzer in the warm water and measure the time. I can drop it in the cold water and measure the time. Now, it could be that the amount of time it takes to dissolve is unaffected by temperature. That's what the null hypothesis says. Or it could be that the time to dissolve is dramatically affected by temperature. That's what the alternate hypotheses say. But all I can do with the dependent variable is I can ask myself, I wonder if I change the independent variable, will the dependent variable change? So I will change the independent variable because I have control over that. And then I'll measure what happens with the dependent variable. Does the dependent variable depend on what's happening to the independent variable? Thank you, people who jumped in and commented. Now, one person said, the amount of water. And the amount of water actually is a kind of variable. But look, I don't know about you. I've been sitting here for an hour and 20 minutes. I need to get up and stretch. Just move around a little bit. I've got to, okay, my back, otherwise I will be crippled. So what I want to do now is I want to take a 10-minute break, all right? So let's take a quick 10-minute break, just to stretch, just to move around a few minutes, and then we'll come back, we'll work on this, and pretty soon we're going to do this experiment, okay? All right, so we are on an official 10-minute break. Radio. 10 minutes. Music lovers, for music lovers, and for summer lovers. All right, folks, sorry. I ended up trying to collect some data. I couldn't resist it. I'm going to shut this down for a second. I'm sure we're back, or I'm back. I don't know if anybody else is back. Hey, but look, here's my little fancy schmancy kitchen thermometer that I have here. And it reads in centigrade degrees or Fahrenheit. I've got a little button here that, of course, it's backwards, right? I can change back and forth, and push the cool button, and it opens up. And just out of pure curiosity, I stuck it in that water that was in my refrigerator, and it was about 9 degrees centigrade, which was like 49 degrees Fahrenheit, which means my refrigerator's not working that well, but it's hot in our house. And then I stuck it in the warm water that was running out of my sink, which was about 45 degrees centigrade. So, you know, I've got a pretty broad range just from doing that. I mean, there's no reason for us to worry about it. Again, you may not have a thermometer like this, and you don't need to have a thermometer like this. But when I generate my warm and cold, I'll be able to measure the temperature, and that, unfortunately, I don't expect for us all to have that data. What I'm going to ask you is, what was the time to dissolve in warm and what was the time to dissolve in cold? And that's what we'll tabulate, okay? And we're getting pretty close to where we will actually do that, which means we might need to modify our experimental design a little bit because most of us have had water sitting there in the refrigerator for more than an hour now, but that's okay. As long as it's, you know, been about the same amount of time, we're in good shape. All right, variables, the independent variable. That's the one we set up. In this case, warm and cold. the dependent variable. That's the one we measure. But whenever you do an experiment like this, there are always a bunch of what has to be what we call controlled variables. Controlled variables, as it says here, are a bunch of should be variables, that must be controlled, otherwise they will sneak in and ruin your experiment. And what I mean here is, for a perfect example here of a controlled variable, somebody mentioned it before, it's the amount of water. Would it be okay to use 100 mils of cold water and 50 mils of warm water? No. The different amount of water could affect the time to dissolve. So what we have to do is control that variable. And it's easy. We just use the same amount of water in both cases. We're going to measure the amount of water somehow. In my case, I'm going to use 100 mils. I'll measure it in here and then transfer it to my cup. Okay. Now, these controlled variables, there can be a very long list of controlled variables, right? It can be there's one independent variable, there's one dependent variable. There could be 20 controlled variables, things that could creep in and ruin our experiment, but we're going to do our best to not permit that to happen. We're going to control the variables by making sure we use the same amount of Alka-Seltzer in both cases. We use the same amount of water in warm and cold. We use the same type of water in warm and cold. We use. Yes, go ahead. Go ahead.
Are we using one tablet or two tablets in the are we going by off the packet instructions where they say dissolve 2 tablets in 4 ounces of water, or are we just using one tablet?
You're going to use 1 tablet in warm and 1 tablet in cold. You bet. So we have 2 tablets. That's what I ask people to acquire, 2 tablets, maybe 3. So 1 tablet is going to go in the warm water. 1 tablet's going to go in the cold water. But I mean, what I'm saying in terms of controlled variables is it wouldn't be okay, for example, to use 1 whole tablet in cold, but half a tablet in warm, right? That just doesn't seem right. It wouldn't be okay to use 1 whole tablet in cold, but then to break the other tablet up into little tiny pieces and use it in warm. I mean, those are the kind of things that if you do them, they will ultimately ruin your experiment, because somebody's going to go, wait a minute, you used 500 mils of water that was cold water, but you only used 50 mils that was warm water. That you've just put a new variable in, which is amount of water. Remember, the research question doesn't say, will Alka-Seltzer dissolve more quickly in a lot of warm water compared to a little bit of cold water? No, that's not in the research question. Research question is basically looking at 2 variables, the water temperature and the time to dissolve. The water temperature is the independent variable. The time to dissolve is the dependent variable. And any other variable that could creep in would any other variable that can creep in will essentially ruin your experiment and cast doubt on your results. So in order to sort of control variables, we just think it through. We go, look, we're going to do this experiment. What's the independent variable? What's the dependent variable? And what are some controlled variables, right? So in our case, controlled variables, things we have to control, otherwise they'll ruin our experiment. That's why I ask people to get 2 of the same size glasses. Hey, can I ask a question? I know this is a silly question, but can you see these 2 glasses right now? Yes, no?
Yeah, I can see him.
Okay, good. You see, I've got to tell you that my computer, all I can see is the PowerPoint. That's it. But in your computer, there's the PowerPoint, and then there's a little photo of me up in the corner or something. I don't see it that way. So I'm saying, look, I got 2 identical glasses. These are as close to identical as I could find, right? I'm going to use the same glass. I'm going to use the same amount of water. I'm going to use the same type of water, tap water. I'm going to use the same stopwatch to measure it. I'm going to use the same definition, same criteria. I'm going to use the same definition of dissolve. I'm keeping all those possible things controlled by making sure they're the same. My science professor, and I'm sorry I didn't put this in here, I don't think I did, is my 6th grade science teacher had something he called the rule of same. And I'm going to write it down, right? This is one of those things I should try. Yes, you can certainly use 2 mason jars. As long as they're the same, that's what we have. Okay, so here's what he called it. He called this the rule of same. And he basically said this. Try and phrase it as best I can. He said, in order to control the controlled variables, you keep them the same. So please write this down, okay? Because I haven't included it in the PowerPoint, and there is a thought question about it. The rule of same says this: in order to control the controlled variables, you keep them the same. You know, it sounds like a silly question, but, yeah, let me just consider this. Sometimes I will ask a question. In fact, it's a thought question. It says, list 2 variables you had to control in the Alka-Seltzer experiment. So we've talked about them. Think about it. What are 2 variables you had to control? Now, I would say we had to control the type of water. We had to control the amount of water. We had to control the type of Alka-Seltzer. We had to control the amount of Alka-Seltzer. We had to control the size of the container. We had to control the definition of dissolve. But you know what sometimes a student will tell me, and I want you to specifically avoid this, is they'll tell me that they have to control the water temperature. Now, why does controlling the water temperature not make sense? And I'll say because of the rule of same. Right? When you control variables, you keep them the same. Is the water temperature the same in both of your 2 containers? I hope not. One's going to have cold water and one's going to have warm water, right? So I'm not controlling that variable. I'm, in fact, creating that variable. That's the independent variable. You can't be an independent variable and a control variable at the same time. Controlled variables are variables that you are going to deliberately make sure they are the same. So they're not actually going to be a variable. You prevent them from being a variable. But the independent variable, well, you know, somebody might think, well, Steve, you're controlling that water. You're making it cold and warm. And I would say, I can't disagree with you, but it's not the same as the word control in the case of this experiment. It's not. Controlled in this experiment means the same, the rule of same. It doesn't mean that I'm manipulating the temperature. That's what I'm doing to create the independent variable. Okay, so this is an important concept that I have managed to not put in the PowerPoint because I screwed up. That's why. So I put it up here on the side. or you can copy it down into your notes because there is a thought question about the rule of same. All right, I'm going to go back here. Independent variable, dependent variable, controlled variables. You know, I'm going to say it again because it's critical, right? I don't have a textbook for this class. And if I had a textbook, then maybe you would read about this in the textbook. And then I would have to answer the questions in the textbook. And I would especially have to deal with some textbooks that use the word educated guess and whatever. You know, I probably said this the first day of class, but I worked for a textbook company for years, and I regularly wrote chapters in textbooks. And when I got them, gave them to the editor would tell me to plump them up, make them thicker, make them put instead of just putting 2 examples, put 4 examples. And it made me a little skeptical about textbooks because once you assign readings in a textbook, you sort of have to assume people are going to memorize that material, etc. And as somebody who wrote textbooks for a while, I'm just a little skeptical about them. I know that they put stuff in there that's just designed to make the chapter thicker and so they can sell it for more money. $150 for the textbook that we use, that's way too much money. And so I don't like to use expensive textbooks. I am sorry to tell you that when you get into 201, you're going to have to buy a textbook that's like $250, and you will have to buy it. There won't be any choice. Anyway, sorry, I'll get off my textbook soapbox. When we do experiments to test our predictions, we are creating our experimental design first. A standard 2-variable question can be relatively easy to answer. That's what the question we're working on. A standard 2-variable question has 1 clear independent variable and 1 clear dependent variable. So here's some 2-variable questions. Are men taller than women? Are cats smarter than dogs? Do starfish prefer to eat snails or clams? Are jalapenos hotter than habaneros? Do cacti grow taller slopes or flat areas? Are college students thinner than high school students? Will Alka-Seltzer dissolve more quickly in warm water or cold water? And these are 2-variable questions, and not every question we have is a 2-variable question. But often, some of the first questions we do in science are 2-variable questions. So let's take this first one just for fun. Are men taller than women? What is the independent variable in this question? I'll let you think about it. What is the independent variable? Remember, that's the sort of thing we set up, a category, let's say. Question is, what's the independent variable in this question? Are men taller than women?
Is it gender?
Absolutely, it is gender. It's gender because we're comparing 2 groups, right? Men and women. Do I need to measure that? No, right? I don't need to measure it. I mean, I'm pretty accurate. Let's say the 95% level. I look at somebody, can pretty much tell about 95 times out of 100 if they're a man or woman. So if I was doing this experiment, as soon as somebody approached me who wanted to be in the experiment, I would say, you're a man, go stand over there. You're a woman, go stand over there. Men on this side of the room, women on this side of the room. It's a category. Okay, so if that's if sex or gender is the independent variable, then what's the dependent variable? What would we measure to get an answer to this question is what I might want to put it. What are we actually going to measure?
The height.
Come on, somebody knows it.
Is it the
Height. Thank you so much. It's height, right?
I mean, somebody else said it first.
Yes.
Yeah. Well, but that's great though. I mean, look, it's this word taller. I mean, I can't look at somebody instantly and know how tall they are, right? It's not that. This is something that really all I can do is measure. So the independent variable is gender. The dependent variable is height. I can't really do anything with the dependent variable except measure it in this case. So I have a group of men on one side of the room. I get rulers out, or I get a measuring tape. I measure all their heights and I write them on the board. I have a group of women on the other side of the classroom. I measure all their heights and I write them on the board. Okay. Now,
Excuse me.
Yes, go ahead.
What age matter? Because I know if you think about it as in different age groups, if you were to take like junior high school girls versus junior high school boys, more than likely the girls will be taller than the boys.
Okay. And so let me come back at you with the question. Does age matter? I think everybody would agree that, yeah, it matters, because we're not talking about, you know, we would have to, let's put it this way. We wouldn't want to have a 3-year-old woman in that group, would we? We wouldn't want to have a wide range of ages in that group. We would probably have to specify that for the group we're looking at, we're going to say, okay, this group is going to be people from age 18 to 50. So what is that variable? What is that age variable? I mean, it's a variable we have to worry about.
Control.
It's a control variable, right? Exactly. Thank you. See, there's a variable that if you, let's say you did this, you actually did this experiment, and then you reported, oh my gosh, according to this experiment, men are taller than women. And somebody said, well, was age, what about age? And you went, oh, I didn't even think about age. They would go, oh, I'm kind of thinking I don't trust your results. Because you included young men, old men, you know, young women, old women. I mean, age is a controlled variable there for sure. So we would have to control that if we did this experiment. We wouldn't define men as any person with an X chromosome and a Y chromosome, and define women as any person with 2 X chromosomes. We would have to we know that in humans, the older you are, well, put it this way, up to a certain point, you grow, and then you kind of stop growing. So, I mean, see, that's an excellent example. Thanks for pointing that out. That's a controlled variable. We would have to control age at some level. And really, with the controlling age would be something like, okay, we're only going to count adults from age 18 to age 30 or something like that. So what about, what about, do starfish prefer to eat snails or clams? All right, this is a good marine biology question from my ancient past when I was a marine biologist. Do starfish prefer to eat snails or clams? What is the independent variable? This one's a little more complicated. I mean, it's categorical, sort of like men and women.
Would it be that snails are on land and then clams are in the water?
No, and I'll tell you why. Because it's just in the water. When I'm talking about marine starfish, they're going to be in the water. So we're talking about marine snails and marine clams. But thanks for saying that, because that occurred to somebody else, I'm sure, too. It's a category, really. And so I'll tell you what it is. The independent variable is whether the starfish ate a snail or ate a clam. Right? It's the category of snail or clam. Now, if that's the independent variable, snail or clam, then the dependent variable is going to be something we're going to count or measure, right? And what are we going to count or measure here? We've got these snails, we've got these clams. What are we going to count in order to answer this question? Again, this question's a little bit more complicated, but it's a nice 2-variable question, really. Oh.
Would it be how much they eat or how much
Thank
starches
you.
are there?
Thank you, thank you, thank you. Perfect. I see. This is the 17-second rule, right? If you wait long enough, somebody will go, "Oh my God, I'm going to say it." And that's right. What you just said was perfect. It's the number of snails or the number of clams that they eat, right? I mean, if I was designing this experiment, I would watch a starfish, and in a certain period of time, I would notice, did it eat more snails or more clams? And
Just wondering, is it actually clams that the starfish prefer eating?
well, in this question, they are. Why? What were you going to say?
That's what I thought I saw like a Discovery Channel thing that starfish like to eat clams.
Oh, well, no, there are starfish that love to eat clams, and there are starfish that love to eat mussels, and there are starfish. Honestly, starfish are pretty well. There's many different species of starfish, and many of them eat, amazing things, right? But the bottom line is, in this particular case, it seems to me as if we're going to look at starfish and we're going to count the number of snails or the number of clams they eat. And that's how we're going to get our data. We're going to go, okay, I watched this starfish for 3 weeks. What a job. And in that 3 weeks, it ate 12 snails, but it ate 56 clams. And that seems to suggest to me that the starfish prefers to eat clams than snails. Of course, if you're going to do science, my first question would be, were there more clams than snails around? Right? And you see what I mean? The bottom line is, though, it's a 2-variable question. The independent variable is snail or clam, what it's eating. And the dependent variable is the count, the numbers. Uh-oh, what did I do there? The count or numbers that you get. It's all you can really do. You could ask a starfish, hey, what do you prefer to eat? But you know what? I've talked to starfishes before, and they don't understand English. Or they don't answer me, or they're answering me in some way I don't understand. But in every one of these cases, there's a nice 2-variable question. Like in this one, are college students thinner than high school students? Well, the independent variable is whether you're a college student or a high school student. And then the dependent variable is your weight, right? So we weigh 25 college students, 25 high school students, we compare their weights, and that's how we have a dependent variable and independent variable. Now, are there controlled variables? There always are, right? There always are. And so we would have to work our way through those. But a standard 2-variable question has one clear independent variable and one clear dependent variable. Okay, here's a question. Do men order takeout food more than women? And I've rephrased it a little because I wanted to make it more answerable and said this: is there a statistically significant difference in the amount of takeout food ordered by men and women? Okay. The independent variable, again, is gender, right? Because we're comparing a behavior of men and a behavior of women. We don't need to measure that. You can look at a person and tell if they're a man or a woman 95% of the time. I'm not trying to be, I don't know, I want to be politically correct here and say, look, I'm not trying to be by gender biased, but we're just doing a mental experiment here, right? So, a man or woman. I mean, we'd have to do a different experiment if we wanted to include, I don't know, transgender people in this or whatever. So, independent variable is gender. Now, what are we going to measure? Well, we're going to measure the dependent variable. We're going to define as the number of times a week that each sex orders takeout food. Are there controlled variables? Oh, I'm sure there are. Just in order to really do this experiment, I would have to sit back, and it would even be better if I was thinking about controlled variables. It would be best if I could talk to some other scientists about it and get their ideas about what controlled variables I need to control so that I don't do a bunch of work and then have a flawed experiment. All right, so when we're doing our experimental design, we're this close to being able to do some Alka-Seltzer dropping. I'm so excited about this. What does the data look like? We have to consider, what does the data look like? How will I measure it? How will I analyze the data? How will I know if my predictions are true or false? Well, what does our data look like? I mean, what actual data, information are we going to collect, or are we going to set it up, and how will we measure it? Well, somebody tell me what some of our data is going to look like. We're talking about the data we're going to collect. What will it look like? I mean, what is it? What is it? The data that we're going to collect.
We have to determine the temperature of our water. Then we also need to determine the amount of water that we're going to put in our container. And then we have
I agree.
to identify the time it dissolves, both in cold or in warm water.
You bet, exactly. So we can stop there. Thank you. The data looks like, for us, it looks like this. We've categorized one glass with warm water, one glass with cold water. So that the kind of data we're going to collect includes data about that has to do with our cold water setup and our warm water setup. The other data that we're going to collect is going to be data on time to dissolve, which we've defined as when the tablet disintegrates. Now, how will we measure our data? Well, we, to a certain sense, we're going to measure our data in the glasses by knowing that we've refrigerated the water for well over an hour, and we are going to run hot tap water to make the other one. Okay. If you had a thermometer and you could measure the temperature, that would be great, but not necessary. We do need to measure the time it takes for the pill to disintegrate. So I'm hoping everybody has a stopwatch on their phone, or they could, you don't necessarily have to use a stopwatch. You could just look at a regular clock and be careful and tell us how many seconds it took to completely disintegrate in warm and to completely disintegrate in cold. So our second set of data is going to be time, right? It's going to be in seconds. One is going to be category, which is warm and cold, and one is going to be seconds. So how will we analyze the data? Well, here's the great thing. When you hear about analyzing the data, people are like, oh my gosh, analyzing the data. But here's the thing, really, when you analyze the data, here's what you're doing. You have to ask the question, which of my predictions were true and which of my predictions are false? Once you have the data, look, here's, where did I lose this? Oh, no, I'm sorry, it's not in here. I apologize. Okay, here's what I was wanting to show you is I wanted to show you the Alka-Seltzer Lab document. Okay, so I'm not sure if it's in this folder. I'll tell you, my brain, I need to remember, either consolidate these folders or I need to memorize these folders better. I don't waste your valuable time. All right, here it is, Alka-Seltzer data at home. All right, we do it all, blah, blah, blah. And before you turn this in, you're going to identify the variables. We've already done that. You're going to write these hypotheses. You're going to write these predictions. You're going to explain your experimental design, what you're going to do. Okay, so here it is. Let's look at our data here. All right, now this data, I just made this data up. But here's what the data sheet's going to look like. In cold water, it dissolved in 67 seconds. In warm water, it dissolved in 73 seconds. All right, let's just assume that's true. This is not what you're going to find out, I assure you. Okay? You're going to find that there's a pretty big difference between the two. But still, let's just say this is the actual data we collected. Well, which of our predictions is true and which of our predictions are false. Because this data right away tells us what prediction is true and what prediction is false. So somebody please tell me which of the three predictions, the null hypothesis, alternate hypothesis 1, or alternate hypothesis 2, which is true? Looking at this data, one of the hypotheses is true. Can I give a hint? How many seconds difference is it between the cold and warm? 7 seconds. Didn't we have a cutoff? Yeah, we did have a cutoff. The cutoff was 10 seconds, right? If there wasn't at least a 10-second difference, then one of the hypotheses predicts there won't be a 10-second difference. One hypothesis makes the prediction that there will be less than a 10-second difference, that they'll basically be the same. What hypothesis is that? Come on, somebody knows it. Maybe I'm phrasing it wrong. One of the three hypotheses that we generated about this experiment says there'll be no difference in the time to dissolve.
The null.
Thank you. Thank you. Thank you. I was counting down in my head, 1001, 1002. It's the null hypothesis, right? Remember that according to the way we set this experiment up, we decided there had to be at least a 10-second difference, but there isn't. There's only a 7-second difference. That's not enough of a difference for us to declare there is a difference. And there was a hypothesis, the null hypothesis, that said there'll be no difference. And the prediction of the null hypothesis said that when we do this and we do that, there will be no difference, according to our criteria, which was a 10-second difference. There had to be at least a 10-second difference. I mean, look, what if this number was 33? Oh, not 333, but 33. What if this number was 33? Well, the null hypothesis, in order for us to accept the null hypothesis as the best, these have to be only 10 seconds difference. So if there's a 34-second difference, then according to our criteria, that is a real difference. And the time to dissolve is less in warm than cold. So what I think is great about this is that when you hear about analysis, it can mean lots of things. But in this particular case, what analysis means is it means you look at the actual data you have and you try and decide which predictions were true and which predictions were false. So we know a prediction is true or false because we have set up the criteria to do it. Now, how will I prevent bias from affecting the outcome? This is an issue we need to worry about. But I'm not too worried about it here, except in one sense. I'll bet most people who are listening to me now think that it will dissolve faster in the warm water than the cold water. And anytime you consider that, somebody might have already developed an opinion, you might need to worry about that. But I don't think we need to worry about it today. Do I need a study group, experimental group, control group? Nah, not for this experiment. So when we analyze the data and establish some conclusions, it's not complicated. We ask, which of my predictions are false? Which one is true? What does the result mean about each hypothesis? Was the hypothesis supported because it made a true prediction? Was it rejected or falsified because it made a false prediction? We can take the hypotheses, look at their predictions. If they make a true prediction, in this one case, then we keep that hypothesis. If it makes a false prediction, we reject it. So here's some essential information. A hypothesis that makes false predictions is falsified, and it's removed from the list. It is trash. We take it off the list and throw it in the trash. Hypothesis that makes true predictions is supported, and it gets to stay on the list. And we might say that's the best hypothesis today, but who knows, we might reject it tomorrow when we do another test. Remember the geocentric hypothesis. It said the Earth is the center of the universe. It made millions of true predictions. So why did they eventually discover it made false predictions? Because somebody really smart was born, or somebody invented a good telescope, and suddenly it was clear it was making false predictions. And the minute it makes one false prediction, it is trash. And that's scary because it means that when a hypothesis is making true predictions, we keep it. We say it's good. We say it's the best. But we can't say it's true because maybe tomorrow it will make a false prediction. And so we just say that is the best hypothesis we have today. We're not going to call it true. We're going to say it is supported. It's been supported by tons of experiments. It's been supported by millions. Moving it up to the level of, say, a theory is not going to happen right away by any means. I mean, I watch these silly crime shows all the time. They march into somebody's house because somebody called them to tell them there's a dead body. They see the dead body. They look at this dead body for what, 15 seconds? And then somebody in that group is going to make this statement. They're going to say, you know, I've got a theory about what killed this guy. And I'm on the couch and I'm like, what? You don't have a theory about what killed that guy. You have a hypothesis. Remember, a hypothesis is just one possible answer to the research question, what killed this guy? It's just one possible answer. He was killed by a heart attack. He was poisoned. He slipped and fell. He was stabbed by a knife. He was shot by a gun. He was killed by an axe. I mean, there's all these hypotheses. But none of those is a theory. And I know my wife says, oh, come on, it's just TV. And I'm like, hey, these are supposed to be forensic scientists. They know the difference between a hypothesis and a theory. They're using the word theory wrong, and that's just me, biology teacher. I told you this already. A bad hypothesis can make millions of true predictions. All right. Hey, guess what? Guess what? I think we're in the position now. Oh, I'm so excited about this. We are in the position now where we can actually do the experiment. Oh my gosh, I'm excited about this. Is this going to be high enough? No, I think I tried this yesterday. Darn.
I think you need 2 Lysol bottles or
yeah, that's right. I need two Lysol containers. And I mean, honestly, I'm not rich enough to afford 2 of these Lysol containers. No, I'm not. So that means I have to use the 1 Lysol container. But uh-oh. Am I still here? I'm not going to use this 1 Lysol container. I'm just going to use this 1 Lysol container twice. I'm not going to drop these Alka-Seltzer in at the same time. I'm not smart enough to measure the time and do it all at the same time. I'm going to drop it in, and I'm going to measure the time and all that. Okay, so I'm going to do it online, but please, here's where you do it too. You just do it at home. If you want to, don't even watch me, that's fine. Just go on your kitchen table and set up the experiment. Warm water in one container, cold water in another container. You get your Alka-Seltzer ready. You get your stopwatch ready. We're going to collect this data, and we're going to come back and report this data as quickly as we can. Okay. I mean, I don't know how long it would take to do this, but I think it shouldn't take us more than what, 15, 20 minutes at the most to do this experiment. I mean, again, I'm going to do it right here and you can watch me, but you know what I want us to collect? I'm going to be asking everybody for data. So, so the bottom line is that in a few minutes, I'm going to say, okay, people, please give me your data. I'm going to eventually make a table to put this data in. All right. Is everybody with me? I mean, if you need to run to the restroom, fine. But the bottom line is we're going to actually do the actual experiment now. I think we've done all the build up to it that we need to. All right. Okay. So it's 3:32 according to my computer. Yeah, sure. You know, the fast relief, let's not worry right now about whether it's cold or sinus or flu or, I mean, I wish they had one that was for COVID-19, but they don't. But when I was a kid, my mom had 5 different kinds of Alka-Seltzer, it seems like. All right. Okay. At home right now, virtually, you're going to do this experiment. Are we ready? Any questions? All right. I am going to be gathering data and doing it right here and getting some kind of stopwatch to time things and all that kind of stuff. But you don't need to watch me, right? You can watch me later on YouTube if you want. Okay. All right. Let's do it. Let's get this data. All right, this is my warm water here in case anybody's paying attention, which is probably not true, but here's my warm water. I'm getting ready to start my stopwatch. Here I go, I'm dropping it in. This is warm water. And remember, I'm going to be very careful to look and identify when this tablet actually disintegrates so I can stop my stopwatch.
Clarification, disintegrate is the one that it's not round anymore, right?
Disintegrate means the pill is gone. Yeah,
Okay.
you bet.
Got it. I'm doing it, but I'm starting with the cold water.
That's fine. You can start
Yeah.
with either. That's fine.
Yeah.
Yeah, almost.
All right, here's my cold water.
Steven,
Yeah,
I finished
ahead.
doing what'd you call it?
Experiment.
Experiment. Yeah. I got a pretty big difference in my times they dissolved in.
Well, I knew that would happen. I mean, I knew there would be a pretty big difference. Just hang on to it. I am focusing in on making sure I can see when the tablet disintegrates in my cold water. That's what's going on right now. And honestly, for me to be able to see whether it's disintegrating, I kind of need to be able to move around a little bit, because it's interesting that in the hot water, it seemed like it just went straight to the top at the beginning, and in the cold water, wasn't a huge difference in terms of temperature, but in the cold water, it's still pretty intact, but it's falling apart.
Yeah, that happens. Yeah, it goes down, then slowly
Ah,
it dissolves. Or
yeah.
great.
Now it's on the surface, but I still see, intact pill. And oh, very close. Very close. Oh, now. Okay. So yeah, I got 31 seconds in warm, and I got 79 seconds in cold. Hey, that's a virtual lab, I guess, huh? That's what a virtual lab looks like. You do the experiment. I'm lying. I've never done that before. I mean, I'm going to tell you, I had already done this experiment in class before we crashed in the spring. And I always was thinking, well, how am I going to do that experiment, in a somewhat meaningful way when we're back online or when we're in virtual? And honestly, it worked out pretty fine. So whoever told me a minute ago about their times, could you tell me what your time was in warm and what your time was in cold?
Yeah, I got it right here in front of me.
Good, thanks.
My warm was 32 seconds and
Okay.
32.51.
Okay.
And then my cold was a minute and 11 seconds and 66.
Okay. So a minute and 11 seconds, which would be, but I'm going to write everything in seconds. So it's 61 point, did you say 66?
No, it would be 61. It would be 71.
Oh, you are right. 71. And was there a remainder? Or?
Yeah, remainder was 66.
Okay, so I'm just going to round that to 7. Okay, who else has data? Who can tell me about their warm water data? Oh, okay, warm, Thelma, it is 22.7 was warm. And what about cold was 59.4? I'm rounding. Thank you. Who else has data?
My warm was 27.67 seconds. And then my cold was 2 minutes and 7 seconds.
2 minutes, so that's 2 times 60 is 120, 127 seconds. Okay, Stephanie, warm is 33 and cold was 126. Thank you. Emily, warm is 25 and cold. Oh, go back. Oh, sorry, I lost it too quickly, but it's up here in the chat line. Okay, it was 25 and 75. Abril was 76.2 and 38. I'm going to round that to 38. 76.2, 38. Travis, thank you. It's
I'm ready when you are.
I'm going to round yours to 26, and 170 is 170 seconds. I'll put it round to 171. Angelique, thank you. It's 3. Warm was really? Is that true? Are these switched?
Sorry, they're switched.
Angelique?
Yeah, they're switched.
Okay, thank you.
Sorry.
So 3 minutes and 20 seconds that's okay. 180, 200, so 200 seconds and 24 seconds. Kendall, go ahead. Cold was 1 minute and 10 seconds, which is 70 seconds. And hot was 30 seconds.
Cold water, it was at 10 point, the temperature was 10.5 C. And
okay. Cold was 10.5 C, okay. And your warm water was?
My warm water was 55.4 C of the warm water temperature.
5.4. Good. Most people won't have these temperatures. I got temperatures too, but it's okay. So hold on. I want to go back. Rocio, it's cold was 1 minute and 10 seconds. So that's 70. And hot was 30 seconds. Alva, the warm was 27.5. And the cold was 169. I'm doing a little rounding here, but thank you. So far, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits of data. Thanks. I mean, again, it's possible.
So would you like my times or no?
Which times, Kendall?
Yes, my cold water.
Yeah, absolutely.
My cold water time.
So go ahead.
My cold water time was 1 minute and 30 seconds.
Okay, so 90 seconds total, and the warm water was
33.6.
33.6. Great, thank you. Hey, this is like a new experience to me. I've got to admit to you, this doing gathering data like this in a virtual format. Never done it before. Seems to be going okay though. That's what's interesting. The only bad thing is I've run out of soda, so I'll be right back. Oh, thank you. Here we go. Zenith, warm 31.2, what are 1.3? Warm 128 points, so that's 88.5. All right, sorry, I had to run away out of soda. I am fueled by caffeine. I mean, I got to admit it. If I don't have caffeine, I start to slowly fade. Especially in this heat. I wonder what the actual temperature in here is. Just kind of curious. I've got my thermometer. All right, who else? Oh, thank you, Alejandra. So cold was, okay, we'll go back, was 1 minute exactly. So 60 seconds for cold and 20 seconds for warm. Very nice. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 people so far. Actually, this is kind of fun. I mean,
Yeah, it was a little funny in my case because I put another I put another tablet in there, but then I forgot to time it.
Oh no.
I did it again in the warm water.
Well, sometimes, you know, so I'm glad you had more than one Alka-Seltzer.
Yeah, you need more than 2, just in case.
The reason I had originally said 3 was I thought, well, maybe I would ask people to dissolve one ahead of time just to look at it because, you know, I know it sounds silly when we're talking about a research question, but I never thought the word dissolve was very, was necessarily that clear. So in this room that I'm sitting now, it's 29.5 degrees centigrade. That's warm. Remember I said room temperature was usually around 20? And I don't need to do the conversion. I could, I think. 84.6 degrees. So it's 84 degrees in here, which, you know what? I'm a Tucsonan. 84 degrees is kind of chilly to me. My house right now is not very cold. So I use my stopwatch, my official class stopwatch, and it worked out fine, and everybody else said it. And I'm waiting. Anybody else who wants to include data in this data set, I would be happy to include it. Okay, but I'm going to jump away for a minute. All right. Well, I'm going to be here, but I'm going to jump away to a minute and try and access something that I should have loaded. Oh, I know. Should have loaded it already. Probably won't take very long to load it. Ugh. Hmm. Oh, there it is. Alka-Seltzer Lab. So this is a little Excel program, and I'm going to actually dump the data in here right now. And this is nice because it will graph it out for us, etc. So just I'm assuming you can see all this. So I'm going to enter the data in 31. 79. 32.5. 71.7. 22.7. 59.4. 27.7. 127. 33, 126. Hmm. Oh, you know what? I can't do this. What am I thinking? Ah, I apologize. I just realized I'm looking at that graph and I'm going, what the heck? That can't be right. So I'm going to have to show you some old data because our data is this. What I'm entering in here, I apologize, is not the right data. Sorry, the graph that I've set up there is not set up to receive data this way. Now, this data, though, is useful to me in another way, and that is what happened to that? Hmm. Now, this is a statistics program, which I'm assuming you can see. Okay. Technical problems. Don't get that at all. Okay, well, I am not going to let that stop me. Okay, I think, look, if you, I appreciate all the data people gave me. I am going to be able to use this data. I don't quite understand, to be honest with you, why it's not letting me do something I want to do. But I'm going to try it. I'm going to try it again. Hmm. Well, that is really interesting. I'm not sure why. Got another possibility here. Hmm. All right. Be patient with me. Now I'll be able to use this data. 31. Yeah, 32.5, 10, 22.7, 27.7, 33, 25, 76.2. Oh, that's back. I think we got that data backwards. I probably wrote it down wrong. 26. Yeah, I must have written a little bit of this data down backwards. My fault. Oh, where was I? 27.5. 33.6. Just plugging this data into a statistical program, that's all. I'm almost done. Okay, now I'm not sure why this is formatted so weird. It bugs me, so I have to reformat it a little bit. Okay, sorry that it's taken me so long to do this, but this is going to be worth it because I'm going to show you something interesting here. All right. All right. Sorry about that. Let me just shrink this. Wait a minute. Let me just shrink this for a minute. What just happened there? Gosh, what did I do? Okay. Sorry, folks. Where am I here? Ah. There I am. Oh my gosh. Everybody's still there. It does show there's 18 people here. I've lost a couple people, but am I surprised? No. Sorry, I'm so feeble here.
Yeah, I'm still here.
Very, very good. All right. So look, the data that we collected was, all there. I mean, it seemed to me as if, everybody did a great job collecting that data. We got some temperatures, like in my case, just for the record, my cold water was 14 degrees centigrade. And my warm water was 35 degrees centigrade. Again, I just use my little, this is what I use to check whether meat, this is what I use on the grill to see whether meat, its internal temperature is safe to eat or, overcooked or undercooked. Anyway, however, I think I spent about $10 for this at Walmart. And it will convert from centigrade to Fahrenheit. It also told me it was 85 degrees in this room, which doesn't really surprise me. Okay, so then, so I got 14 degrees cold, 35 degrees warm. Kendall also had a thermometer like this, and he had his warm was, oh, wait, let me get this again. Kendall, is this right? Your warm was 55.4, and your cold was 10.5?
Yes, sir.
Yes, excellent. So the difference in my case was 20 to 21 degrees, and the difference in your case was 44 plus degrees, right? I mean, so we were able to create a pretty wide range. In fact, as I said, when I did this in a classroom, I have ice water, so people have water that's 2 or 3 degrees, and then they have warm water that's been generated either from the tap or it's been generated from a flask that I warm up, but I deliberately never let it get higher than 55 degrees. I mean, you have some pretty warm water coming out of your tap there. 55 degrees is pretty warm water. Again,
I use a kettle at home.
Oh, did you? Oh, so you use some pretty warm water.
Yes.
And that's great. Okay, so here's what I was trying to do, and that it didn't occur to me, right? Is I was trying to put that in a graph where on the x-axis was the independent variable, which was temperature. And on the y-axis was time, okay? And that seems totally logical, except that we didn't actually have any real temperatures. We just had two categories, warm and cold. So I started entering that data in, and I looked at what it was generating, and I went, no, this isn't right. And then it hit me, oh, yeah, this particular system was set up to receive a number like 2 degrees centigrade and 120 seconds. You see, it was points like that. So fortunately, dementia hasn't totally conquered my brain yet. What I did instead was I went over and I activated an attached program that ran a statistical test, but also did a little histogram like this too, okay? Now, before I show you the histogram, I want to go, before I show you that, I'd like to go back to, I'm going to shrink this, and I'm going to go back to this one here, and go back to sheet 1. And this is not our data, okay? It's not our data. It is data collected in a classroom at Pima just not that long ago. Well, a while ago, right? I've been collecting this kind of data for a long time. So anyway, take a look. Just understand this is not our data, but look over here. Here's temperatures. 8 degrees, 33 degrees, 8 degrees, 32 degrees, 5, 50, 60, 0. These are temps in degrees centigrade. Notice the range. It goes from 0 degrees to 60 degrees, okay? Now, that's what's graphed out here, and you can really see it. Here's 0, and here's 60, okay? So we've got those graphed. Remember, the independent variable always goes on the x-axis, and the independent variable, of course, was water temperature in this particular case. Now, we just had warm and cold. Now, the time to dissolve, it goes on the y-axis. So the independent variable goes on the x-axis, the dependent variable goes on the y-axis. And so it took all this data, and it's not sorted in any way, and it graphed it out. Each one of these blue points represents one of these data points, right? Like this one looks to be about 30 degrees and 40, low 40s. So here's 30, 42.7. So that's probably that data point right there. But then what I think is cool is, look, it drew a line. This is a program, it'll estimate the line. It plots a regression line, which I am not going to ask you to do anything like that. But what this regression line is interesting is, what I think is interesting about it, is that we could have generated predictions that were graphical predictions. And in a graphical prediction, the null hypothesis prediction that says there's no relationship between time to dissolve and water temperature, it would just be a straight line that goes across here. It would just be a straight line, because it would basically say, it doesn't make any difference what the water temperature is, it dissolves in 70 seconds. It'd be a straight line. Well, we don't see a straight line. That suggests we should reject the null hypothesis. Now, another line would be this line, a line that went this way. It went from this corner up this way. And that says that as the temperature increases, the time to dissolve increases, right? And it's because it goes up this way. Time to dissolve, temperature. This line here would say as the temperature increases, the time to dissolve increases, which means it dissolves slower in warm water. That's what that line would have represented. Okay?
Correct.
But of course, that's not what the line looks like. So we're going to reject the hypothesis, that we're going to reject the prediction that says that as temperature increases, time to dissolve increases. That's a false prediction. We're going to reject that hypothesis. In fact, the line looks like this. I mean, that's what was graphed out. My line looks like that in this data set, which is similar to ours. And it says that as temperature increases, time decreases, right? As we go this way, the time to dissolve decreases. That is good hard data that suggests that one of the alternate hypotheses made a true prediction. The alternate hypothesis that said that that it will dissolve faster in warm water. That's what this line represents. And this line shows that one of the hypotheses made a true prediction and one made a false prediction, and the others made false predictions. Now, again, I wish we did this, but this would have required us to all have a thermometer, which we don't have. Okay, so now let me show you this. Oh, by the way, any questions on this? I'm not going to ask you about graphical predictions, but I thought it would be useful to realize the line would look like this if it was a null hypothesis. It would look like this if it was one hypothesis, and it would look like this if it was another hypothesis. We could have pictured that out a priori as a prediction, no doubt about it. Okay, but let me show you this. This is interesting. This basically shows our actual data. This is our actual data. Okay, just to be clear, this is our data. I just want to make this a tiny bit smaller. Oh, perfect. All right, so this is our data. And you'll recognize that over here, this column, 31, 32.5, 22.7, etc. This is the data time to dissolve in warm. And over here, 79, 59, 170, 200. This is the time to dissolve in cold. I mean, I've labeled these columns up here. Warm, cold. Okay? Now look up here. When I plugged this in here, because it's a statistical program, it told me the average. The average time to dissolve in warm was 28.8 seconds. And the average time to dissolve in cold was 102.1 1 seconds. Does everybody sort of see that? I know it's tiny. Pretty big difference in the average, and averages are pretty powerful things, really. So now take a look. It graphed that out the only way it could graph it out, as a histogram, so a bar graph. So it's basically saying here's the average for cold, here's the average for warm. Oh, did I get that backwards? I think I did get that backwards. I did. This is the average. Oh no, I guess I got it right. This is the average time to dissolve for warm, and this is the average time to dissolve for cold. I did get it right. Yeah. So look, this, and so that's the average right there, right? Average. Now, this bar that's here, just for the record, it represents a measurement of the error, right? It's a standard deviation, which is kind of an error at some level. It's the average deviation from the average. But take a look. This error line here, and look at this error line here, tiny. This says that there was more variation in the warm water measurement than in the cold water measurement. But take a look, this line and this line, they are nowhere near overlapping, okay? And I'll tell you what that means. The data's right up here where it says the p-value 0.000. What this says is that the data we collected, that there is a statistically significant difference, highly statistically significant difference between the time to dissolve in warm and the time to dissolve in cold. So this is a kind of statistical test called a t-test. And a t-test is a pretty powerful test that uses averages. And averages are pretty powerful numbers in many respects. And so what this shows is that even in the way we did it, you know, we had to set it up a certain way to do it virtually, we still were able to demonstrate a highly statistically significant difference between the two groups. And that is sort of meaningful to me. I mean, it means that we are pretty clear. Now, look, there is a statistically significant difference here, right? And certainly that's going to be reflected in other realms. So let's go back. I've got to remember what I'm doing here. Let's go back to what am I doing here? Oh, all right, sorry. All right, so here's your paperwork, the paperwork you're going to complete and it turn into me. And let's just make this paperwork due by Monday. Okay, there's no huge rush. What you're going to do in this paperwork is you're going to fill out this part, the variables, the null hypotheses, predictions, etc., based on your experiment, the experiment that you did. Now, again, in my case, I'm going to just plug in my real data here, which is in cold, it took 79 seconds. And in warm, it took 31 seconds. All right, that's my data. But you have similar data to that, I'm sure. Okay, so here's my question. Look at my data. Remember that my null hypothesis, go up here, my null hypothesis for this experiment is going to say this. It's going to say there is no difference in the TTD in cold and warm water. Okay. My alternate hypothesis is going to say this. There, oops, there, backspace, is a difference and Alka-Seltzer dissolves faster in cold water. And then down here, I can just copy and paste this. So there's less chance for me to screw it up. There is a difference, and the Alka-Seltzer dissolve faster in warm water. Okay. So, can I ask, does everybody understand where I got these hypotheses? Oh, I guess I should have plugged in here. Difference in the TTD. Difference in the TTD. Oh, I see. I'm wondering, why did one go over and the other not go over? Still got that question. There's a difference in the TTD faster in warm water, cold. I guess warm's bigger than cold. That's it. All right, no problem. I can solve this problem easy enough. Not that it's really a problem. Okay, so I'm hoping everybody looks at these hypotheses and goes, Steve, I totally understand these hypotheses. Okay, now the null hypothesis is going to sound something like this. If the null hypothesis is true, then when I dissolve one Alka-Seltzer tablet in cold water and one Alka-Seltzer tablet. Okay, I dissolve one Alka-Seltzer tablet in cold water and carefully measure the time to dissolve and one Alka-Seltzer tablet in warm. Remember, our criteria was 10 seconds. So here's the prediction. I started with if the null hypothesis is true, then when I dissolve one Alka-Seltzer tablet in cold water and carefully measure the time to dissolve, one Alka-Seltzer in warm water and carefully measure the time to dissolve, there will be no difference in the time to dissolve. Remember, the criteria we used was 10 seconds, right? Hopefully everybody's with me. Now, for what it's worth, I can just copy this, paste it down here. If alternate hypothesis 1 is true, blah, 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 blah. There will be a difference in the time to dissolve, and it will dissolve faster in cold. Back up here, Steve. Cold water. Hey, everybody see how I got that one? And then the other option, of course, going to be easy, is copy this, post it down here, post it down here. And the difference is I'm just going to have to change this one word. There we go. There's my predictions, very quickly laid out. If the null hypothesis is true, there'll be no difference in the time to dissolve. If alternate hypothesis 1, there will be a difference, and it will have dissolved faster in cold water. And prediction of alternate hypothesis 2, there will be a difference, at least a 10-second difference, and it will be dissolved faster in warm water. Everybody see that? I mean, this is what you're going to do when you do your experiments. So, I mean, the bottom line is that, you know what? Go ahead. Somebody have a question or comment? I'm deliberately leaving these up so that if you wanted to just look at them, stare at them for a minute, because I'm going to ask, you're going to have to fill these in. But you know what? I shouldn't have to leave these up very long. You know this stuff super well. All right, so let's just remember. Go ahead.
Do you want it like super precisely, like how you did it, like how you word everything?
Well, here's the thing. It does not need to be worded exactly like I worded it. But it is probably true that the way I've worded it, it is relatively precise, don't you think?
Yes.
Well, and the reason is simple. I've generated 1 million hypotheses and predictions in my life. So, I mean, it flows off my tongue very easily. I'm leaving this up here briefly so that if somebody wants to take a screenshot of it or write it down, they can use it as a model. Does it have to be exactly this way? No. In fact, you know, your alternate hypothesis 1 could be that it'll dissolve faster in warm water, and your alternate hypothesis 2 could be that it's going to dissolve faster in cold water. It's your hypotheses and your predictions. But I do I do think it has to be something like this, which is why, again, you know, I'm leaving it up here. So for a second, I'm not going to leave it up much longer. I'm leaving it up here in case somebody wants to take a screenshot of it or wants to at least copy down what one of these predictions would look like. Now, did I mention that no one's going to win the Nobel Prize for this experiment? Because it's just, you know, it's just not that way. It is a very, very simple experiment. So you won't get the big bucks. I've been forgetting to use my sound machine. Thank you. Thank you, thank you. Thank you. Wow. That was a lot of applause. All right, here we go. Now I'm going to jump down. I'm hopefully going to remember this. I'm going to jump down to my data. Here it is. Here's the actual data I collected. Is there a difference between the time to dissolve in warm and cold according to our criteria? Is there a difference according to our criteria? Yes, you bet.
Clarification first.
Okay.
Why are you using 10 seconds? Is that stated in your null hypothesis or somewhere?
No, you know why I'm using 10 seconds? Because when we were discussing this...
Because your data earlier was...
Yeah, when we were discussing it yesterday, someone suggested that 10 seconds would be good. So
okay.
That's why. I mean, look, if we were doing this in a class where I had people working together in groups, right? Remember when we used to actually be able to go to a classroom? Oh, those were the days. Thank you. Anyway, the reason is somebody suggested 10 seconds. But if we were in a classroom and we were working in groups, I would have told the groups, look, you figure out what your criteria is. And in my experience, just having done this before, is groups usually choose numbers like 5 seconds, 10 seconds, 20 seconds, 30 seconds. They choose numbers like that.
Okay.
And if you look at this, even 30 seconds would be they would still reject the null hypothesis, right?
Okay. Yeah. Gotcha.
So in this case, there is a difference. So that means there is a clear difference according to our criteria, and that means the null hypothesis has made a false prediction, and the null hypothesis has to be rejected. The null hypothesis has been falsified. The null hypothesis is now in the trash can. Okay? All right. Now, there is a difference. So that means that one of the alternate hypotheses has made a true prediction. And the difference suggests that it took 79 seconds. This was just my data, right? 79 seconds in cold and 31 seconds in warm. It took, a difference of 48 seconds difference, and it clearly dissolved faster in warm. Okay? There is a difference, and it dissolved faster in warm. So I'm going to go back up here again. I'm going to ask you. Computer, please behave, computer. All right. Look at these two. We already rejected the null hypothesis, didn't we? We did. And then, so look at the other two hypotheses and the predictions they made. Which one of these will we reject? One of these two, we have to reject it. Somebody tell me, are we going to reject
the null hypothesis?
Well, we rejected the null hypothesis already, and so it's gone. It's in the trash. So now we've just got alternate hypothesis 1 and alternate hypothesis 2. One of these made a true prediction, and one made a false prediction.
H2.
The first prediction?
Well, hold on. H1 said it will dissolve faster in cold water, and I think what you're saying is we have to reject H1.
Yeah.
Yes.
You bet.
Based on your experiment.
It made a false prediction. But alternate hypothesis 2, it made a true prediction. So technically, for what it's worth, this one gets thrown in the trash, this one gets thrown in the trash, and this one has made a true prediction.
It is accepted. Okay.
We keep it. We would say, based on, I would be very careful and say, look, based on the experiment we did, we are going to reject the null hypothesis, and we're going to reject the alternate hypothesis 1. And that they made a false prediction, so they are gone. But alternate hypothesis 2 that said that there will be a difference and it'll dissolve faster in warm water, that made a true prediction. And all that means, to be honest with you, is it means that as of right now, based on the data we collected, we accept alternate hypothesis 2. We say it has been supported. But I'll tell you what we will never say, right? I mean, we would say here, just copy this over. The prediction of alternate hypothesis 2 is true. Prediction was true. And the alternate hypothesis 2 is accepted, slashed, supported, slash, the best today, right? Tomorrow, who knows what's going to happen? And honestly, this is the nature of science. This is the nature of science. When we do good science, we are very, very careful. And again, if I was to ask you, why don't we just declare this true? Well, I hope you would say, well, Steve, you told us that a hypothesis can make 1,000,000 true predictions and not be true, because it could make a false prediction tomorrow. So that's one way you could put it. One science mentor I had, I don't remember who it was, said to me that you can never declare a hypothesis to be true until you have tested every prediction it makes. Every prediction it makes. And how many predictions will a good hypothesis make? Millions, millions and millions and millions. And so unless you want to devote your whole life to testing the millions and millions of possible possible predictions, then you're never really going to be able to declare it to be true. Now, of course, in science, when we're trying to answer basic questions, we are very careful, because sometimes the best answers we have are actually not the best answer. Again, I would look at the geocentric hypothesis that I've talked about, right? But eventually somebody noticed that the geocentric hypothesis was making false predictions. And that is, once a hypothesis makes a false prediction, it's considered a bad hypothesis and trash. You know, I don't know if you've ever heard this story, but probably you have. I know people who are kind of like astrological people, and they will tell me, they'll say this to me sometimes. They'll say, Steve, I know why everything's going crazy and screwy today. Maybe you've heard this before. And I'll go, why? They'll go, well, because Mercury is retrograde. I don't know if anybody's ever heard that. Mercury is retrograde, which means it's going backwards in the sky. It's not going forwards like it's supposed to go forward. Well, the reason I mention that is not just to tell you that I think that's totally crazy and unscientific, but that's actually a throwback to about 500 years ago, or maybe more like 200 and some odd years ago, when astronomers discovered that some planets were actually moving backwards. The geocentric hypothesis says planets cannot move backwards. As soon as an astronomer collected the data and said, look, here's a planet moving backwards, it's retrograde motion. Well, actually, that immediately rejected the geocentric hypothesis because it made a false prediction. But what was actually said at the time was, oh no, that's not true. When planets are moving backwards, that's evil. It's an evil time. It's Satan trying to confuse us. It's questioning our faith, because they actually incorporated the geocentric model into some religions. And so even to this day, I mean, we're talking hundreds of years later, there are people who think that when a planet moves backwards in the sky, which is totally normal when you're not the center of the solar system, sometimes the planets go past us, and then as we catch up with them, they seem to be going backwards. It's just pure astronomy. They still hang on to this idea that there's this evil condition in which the planet is retrograde because it dares to question the truth of the geocentric hypothesis. Sorry, I'm going to get off my soapbox. Great, but everybody's had plenty of chance to look at these predictions, and then again, I went down to my, now here's where you're going to explain your experimental design. You're just going to tell me in great detail what you did. Okay. Then you're going to use a chart like this and fill it in. Then you're going to explain the analysis of your results. I've made that very easy, which predictions are true and which predictions are false, which hypothesis is supported and which hypotheses were rejected. Since there's three, you know, they can't all be the same. They can't all be true. And they could all be false. And then that just means that on our list of hypotheses, we didn't include the best ones. But they can't all be true. Okay. So this thing where you're going to fill in all the rest of it, giving me a headache. I am going to ask for that to be due by Monday. Okay. So I'm going to go up here to this. I'm going to include a new line in it. Okay. Alka-Seltzer. Thank you. I'll figure that out. Alka-Seltzer Lab due Monday. You know what? I'm going to make it due Monday after class. So just in case anybody has some questions, so I'm going to make it due Monday at 7 p.m. Okay? That way, if somebody doesn't generate a question that they need to have answers for me tomorrow, they can still ask me about it on Monday, and then finish it up, put the finishing touches, and send it to me. Now, I think it's posted as an assignment, and therefore you should be able to fill it in and just submit it on D2L.
I clicked on the assignment for the lab, and it said error, like it wouldn't let me click on it.
Oh, really? So on D2L?
Yeah.
In D2L. Okay, so let's, while we're here, I'm going to have to log in again. Everybody see my password? I'm going to go right to D2L right now and check it out. Because I don't, you know, I mean, I appreciate it. Believe me, if you had that problem, then somebody else had that problem too. And so we're fortunately in a position where I can just jump to D2L. I can go to the beautiful forest. Oh, whenever I look at this forest, I think I want to go up on Mount Lemmon. Because I don't know what it's like up on Mount Lemmon now with all the stuff. So I'm going to go down to assignments. And Alka-Seltzer Science. Let's see what happens when I just click on it. You know what? Let me go back again. Sorry. I'm going to do what I can. I'm going to try and make myself a student. Well, I appreciate whoever told me I could make myself a student on this. Nobody ever told me that before. Maybe I didn't ask the right question, but here we go. So now I'm down and I'm going to open, see if this will open. There it is. You know, here's the thing. If it didn't open, I would try it again. So it did open fine for me, right? That doesn't mean it opened fine for you. So I'm going to, again, show you that there's always an alternative way to deal with this, right? That was D2L, which is great. But the alternative, of course, is to go to my courses. It's just loading. Go to this class. Go to Drive. go to the folder, Bio 156 Summer Session B 2020, and then here's the Alka-Seltzer Lab, and it just downloaded it, so I have to open it up. Once I've opened it up, I can go up here and hit Enable Editing. Well, I could print this out and fill it in by hand. I could fill it in, save it, and then send it to me as an attachment, smacky@pima.edu. So I'm deliberately, because I'm new at this, I'm deliberately, hold on. Is this the one I've been playing with? Yeah. Oh, yeah, I'm going to save this one. All right. So there's alternate ways to get this stuff. That's what's important. And again, if I was a more sophisticated instructor and I knew more about these systems, then maybe I wouldn't have to do an alternate way. But I'm happy to accept things by email. And I'm happy to accept things on D2L. And I actually need to spend several hours doing the grading and get that stuff loaded, and I'll do that as fast as I can. On some people, I've already loaded some grade data in because it's just very time consuming to grade things this way. That's all. I have to admit, it's easier when you have a piece of paper in front of you and you can look at it and grade it and make notes on it. It's much easier, but we don't have that now. And I'm not asking anybody to send me paper.
I have a question, Stephen.
Even though yes, go ahead.
So for us, after we finish the lab, and once we have once you turn it in, do you want us to have it as a PDF or as a Google Doc or the Word doc?
You can do any of those. I can handle PDFs, Google Docs. So whichever is the most convenient for you, I'm happy with it. Okay, so I can handle any of those documents. Again, though, I mean, I'm going to admit that handling documents this way is it's much more time consuming than it is if I just had a piece of paper in front of me. But I'm going to get stuff caught up fast as I can, so you know what your grade is. I mean, honestly, on these first couple of items, I would be astonished if people didn't do very well on this quiz and didn't do very well on this lab, and basically I'm anticipating that when I've got all these grades entered, there's going to be a bunch of A's, and that's fine. Keep those A's. That's fine by me. Okay, just a matter of doing that.
And
thank you. Welcome.
Can you also see like the assignments that we turned in through D2L? Can you still see that, or are you still trying to familiarize with D2L? Okay.
Yes, I can see them pretty well, as far as I know.
Okay.
But you know, I mean, I have to admit something to you, and that is that I'm going to try and be pretty strict about the quizzes, because I'm going to post a key to the quiz, right? So I have to sort of be strict about the quizzes, because I don't want to post the key and then if somebody just copied the key, they won't have learned anything. I mean, as it is, they're open note, open book, 48 hours to work on them. So, but you know, I feel, how do I put it? I feel a little like I need to be flexible as much as I can when it comes to turning in these documents, because there's always potential glitches in email, and there's always potential glitches in D2L. I mean, there's glitches. And those glitches can mean that somebody did their best job to turn it in, and somehow it just didn't turn in right. And that's, you know what? I want to be as flexible as I can about that. You know, I have to take it on a case-by-case basis. So that's the only way I can actually, you know, think about it being fair, because of the, you know, if I was like a total and complete expert on D2L, and I could explain everything perfectly, which I know people that are like that, but I would probably feel maybe a little bit more hardcore about it, but I need to be a little bit flexible. So anyway, that's on the record, right? It's recorded, so you could always go, Mr. Mackey wasn't flexible with me, and look, here's a piece of video that says he will be flexible. All right, so so anyway, that's the next assignment. So I want to go, you know, we looked at a lot of stuff today, absolutely. right? And I want to go here to this PowerPoint. And I'm actually pretty close to done with this PowerPoint. So look at this. I don't think we need to talk about this page. We already talked about it. So what's next? Well, some information we've already discussed. And you're going to have this right in front of you. A hypothesis that makes false predictions is falsified, rejected, and is removed from the... I mean, if a hypothesis generates predictions about measurable, countable, weighable things, and then you do an experiment and you discover that it has made a false prediction, well, then we don't want to keep that hypothesis around, right? We live in science, we live in the realm of the countable, measurable, weighable. If we discover that something has made a false prediction about countable, measurable, weighable stuff, well, then we reject that hypothesis. If it makes true predictions, we say it's good. Today it's good. It's great. We could say we love it, we like it, it's our favorite hypothesis, but we're not going to say it's true. Sometimes when you can do an experiment and reject all the hypotheses and go, hey, wait a minute. We have no hypotheses left. What does that mean? It means you need to go back to the drawing board. You might also need to rethink your original research question, hypotheses, predictions, your experimental design. It's possible. If you reject all the hypotheses, which can happen, not in a simple experiment like we just did, but in some experiments, you reject all the hypotheses, well, then you have to go, you don't just give up, go, well, that's it, I'm going to go to my Ouija board. No, you go back and think, okay, I guess the best hypothesis was not on the list. Let's think about the list again. I told you about this disturbing idea already. No reason to think it up. Peer communication, you know, we've actually already looked at this. Oh, you have access to this PowerPoint. We've already looked at this, etc. Last thing on this PowerPoint day, and we're going to call it a day, is I want to show you a document. This is the last thing on this PowerPoint. It's called, How Does the Hypothetical Deductive Scientific Method Help You Avoid Being Misled as You Search for Answers to Your Questions? And I have to tell you how I generated this list. I was working in a lab at the U. I was reading an article in the New Yorker magazine that said that scientific method helps you avoid being misled as you search for answers to your questions. And I thought, well, that's interesting. What it means is it helps keep you on track. And so I happened to be at a brown bag lunch with a bunch of scientists, smarter people than me by far. And I asked them, I said, look, before you run, can I ask you a question? How does the scientific method help you avoid being misled as you try and answer your questions? And here's a number of things they told me. They started just telling me this stuff. I was writing as fast as I could. Number one, it provides a time-tested, systematic method to follow. That's the hypothetical deductive scientific method. Type of critical thinking that you know about now and you can use in your own life. It assumes you will interact with other scientifically trained peers right from the beginning. That's peer communication. It insists that you consider how the research question is worded. It has to be precise and clear. It insists that you consider multiple possible answers. Of course, I mean hypotheses here. It insists that you make and test predictions about the countable, measurable, natural material world. You know, you can't answer a question like, are there more ghosts in a Walmart or in a cemetery? The reason is that I can identify a Walmart, I can identify a cemetery pretty clearly, I think. But how can I count ghosts? There is no ghostometer. And so even though I might generate a research question and generate hypotheses and predictions, and hypotheses, as soon as I ask the question, is it testable? Well, then I realize I can't do science on it. I can't do science if I can't count, measure, weigh things. So does that mean I can't answer the question about whether there's more ghosts in a cemetery than there is in a Walmart? Well, technically, I would say it doesn't mean that, because that's when I drag out my Ouija board and I bring my Ouija board to Walmart and I ask it, how many ghosts are in this building? You see what I'm saying? But you can't use science to do that, because science means counting, measuring, weighing. Okay. It insists that you examine possible biases. We didn't worry much about this, but human beings, they have a great ability to alter outcomes of things. They have a great ability to construct reality. And so we need to think about it. It encourages internal and external repeatability. Internal repeatability means that we often do an experiment more than once. Hey, today, in order to get a clear picture, how many experiments did we do? Well, I collected data from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 people. We did the same experiment 15 times. That's internal repeat. And now external repeatability means that we produce an experimental design that's so clear that someone else could do it, you know, around the world. They could do it around the world and they would be able to get the same results, hopefully. Number 8, scientific method insists that you think about variables, control groups, controlled variables. What's the independent variable? What's the dependent variable? And number 9, this is the last one, there were probably more. Scientific method always reminds you that you will never be 100% sure your answer is correct. You should always keep an open mind. And really, when I think about that, I want to go all the way back to here, which says that, oh, maybe by here, that a bad hypothesis can make millions of true predictions by accident before it's ultimately rejected. Therefore, if you're really doing good science, you need to be aware that that can be true. And so you're going to be careful. You're not going to declare that the ultimate truth of the universe is that the earth is at the center of the universe. I mean, you might say, look, there's, based on 1 million experiments, there's a lot of support for the hypothesis that the earth is the center of the universe. Okay? That's what you might say. That's not what they said. They basically, I mean, look, you know the geocentric hypothesis. I mean, most people know this. People were put to death for promoting it. Galileo Galilei, right? Very famous scientist. He was arrested and probably tortured. So he would recant his declaration that the geocentric hypothesis was false. It was rejected. I mean, this guy went to prison for that. So, you know, there was some pretty harsh, you know, people said, look, don't even tell us that's not true because we know it's true. Well, no, you didn't know it's true. If you had done real science, you would have had it as a hypothesis and just left it there. Oh. There we go. Now, of course, you have this PowerPoint. So before I shut it down, I better ask, are there any questions about any aspect of this PowerPoint that I can answer? You know, I'm going to tell you this, so this is probably me bragging, but I think this is one of the best PowerPoints I've ever put together on the scientific method. I really do. Is it perfect? No, I think I need to rearrange some things in it, but this is a pretty darn good PowerPoint on the scientific method. It's one of the best ones I've ever seen, and that's, well, again, it's not just because I put it together, but I did try very hard to create an exceptionally good and clear PowerPoint. So you now have that PowerPoint, and you feel free to use that PowerPoint when you're trying to educate your friends and family about the scientific method. Feel free. I give you my permission to use it. All right. No questions are appearing. I'm about to click the X. Ah, here we go. All right, people, I'm done. I'm worn out. I'm Alka-Seltzered out. I don't know how you are, but okay, go ahead, Alva. What's the question? Oh, the question is the independent variable, can it be described as the water temperature? Yes, that is what the independent variable is, water temperature. And I know I said this before. I said, look, I might ask you a question, and probably will on this next quiz, about what variables did you need to control? And please, nobody tell me water temperature, because water temperature is the independent variable. It is not a controlled variable. Even though you may think, oh, I'm controlling it because I'm putting warm in one and cold in the other. Well, that may be true in a broad sense, but when you use the word control in a scientific experiment, it has a very specific meaning. It means the rule of same. We keep controlled things, we keep the same. Same amount of water, same size container, same amount of Alka-Seltzer, same timer, right? Same definition of dissolve, same criteria. You know what I mean? Water temperature, we definitely didn't keep it the same. We deliberately made it different because that's what scientists do when they create the independent variable. Okay? Well, anyway, I think we all deserve a round of applause for your hard work today and putting up with me for what? 4 hours. I can't believe it. I'm amazed. All right, so here it is, a round of applause. Thank you. And I have yet to tell a really bad biology joke. But when I do, I'm not going to wait for anybody to actually laugh. I'm going to use my sound machine so I don't feel horrible. Okay? All right, people, I'll see you tomorrow at 1:15. Have fun working on that lab. I'll see you tomorrow. Actually, before I leave, I should probably stop the recording. Stopping the recording, though. You can go away now.